Hi everyone, welcome to Understanding OS One Concept at a Time. I am Sandeep. In this series, we will take a deep dive into the world of operating systems, but in a way that's clear, simple, and easy to follow. Now, let's be honest. When most people hear the term operating system, they either think of Windows or Linux, or just imagine something too technical to care about. But the truth is, the OS is the heart of your computer. It decides who gets to use the CPU, how files are stored, how apps talk to hardware, and so much more. This series is designed with one goal in mind: to make operating system concepts understandable, one idea at a time. Each video in this playlist will focus on just one concept, whether it's memory management, system calls, CPU scheduling, or even file systems. And we won't just stick to textbook terms, we will use real world analogies, animations, mini stories, and even restaurant or office examples to help you remember and visualize each idea. So, whether you are a student preparing for exams, a teacher looking for a better explanation, or just someone who loves to learn tech, you are in the right place. By the end of this journey, you will not only understand what an OS does, you will think like an operating system itself. So go ahead and hit the subscribe, and let's begin with our first concept in the next video. This is understanding operating systems one concept at a time. Let's make learning simple. Thank you. Hi friends, welcome to this introductory session on a new series, Understanding the Operating Systems, One Concept at a Time. So, this introduction tries to give the overall idea about what an operating system is. So, in order to understand the fundamentals of operating system, we can just try to look at a correlation between the restaurant working and how a computer system works. So let's dive into what the operating system is. Operating system is one that manages computers, hardware, and software resources. It provides a user interface and enabling communication between the user and the computer. It provides a platform to run applications and manage the resources like memory, CPU, input-output devices, and so on. So in short, operating system is a software that is between a user and the machine, and it provides all the facilities to the user so that with minimum troubles, a human can interact with the machine. So that is possible with the operating system. So when we talk of a computer, it is made up of many systems, subsystems, like a processor, memory. Again, in the memory, it can be a memory inside the processor, memory outside the processor. In the memory outside the processor, it may be on the motherboard or on the background. So the memory inside the processor we call cache memory, the one which is on the motherboard we call it RAM, and the one which is in the background we call it secondary memory. So under secondary memory we have many, like a hard disk, CD drive, and many more. Then this whole documents or our processes or the programs have to be stored in this secondary memory, and this storage of the secondary memory should be such that it is easily accessible and should be efficient. So to interact with the machine, we do require some I/O devices. So we need to understand what the I/O devices are and how they help us in interacting with the machine and how they simplified our world of interacting with the machine. All that. Then the next issue we talk about is about the security issues, access control, and when we are working in a big team, then we would like to interact with each other. So some networking required and all that. So looking at that, we have divided our operating system into various components. So the operating system is one which is between application written by the human or the user and the machine or the hardware. Hardware is an electronic device which understands only zeros and ones, and it has its own language, which we call machine language, and it is highly complicated for a human to interact with the machine in the machine language. Therefore, we would like to simplify the actions, and that simplification is done through the applications. And these applications, in turn, make use of the operating system to interact with the real machine. So the various components of operating system. So if we just look at the block diagram of the operating system, we have hardware at the foundation, and then we have various components of the operating system. Then they are used through the user program, and user program you connect to the system through the user interface. User interface makes use of the system calls, and these systems call will activate one of these components, and through these components it goes into the hardware, and that's how it communicates with the hardware. So to understand the various components here, we just list down what all are there. So we have multiple programs to be running simultaneously using maybe a single CPU or multiple processor, whatever it is. We make sure that all the processes are run efficiently without disturbing each other. So to make sure that everything runs smoothly, we do require something called process management. Then we have different types of memories, and to efficiently use the memory so that the overall performance of the system improves. So that is taken care by the component called memory management, and other programs and all the various documents which we want to save in the secondary memory have to be stored in the form of files, and storage of the form in the secondary device, and getting the files from the secondary onto the primary and making use of it has to be done more efficiently, so that activity is taken care by the component file management. So various devices are connected to our system like keyboard, mouse, monitor, and many more such things, and each one has its own way of working, so we must ensure that the working of each device is done correctly and efficiently. So to make sure that all devices are connected to the system efficiently and they are working with their full efficiency is taken care by the operating system component called device management. Then we have user interfaces where user wants to interact with the system. Yes, of course, security is one of the important issues. Want to make sure that the files are not corrupted either by virus or by any invader. So we must make sure that all our system are under surveillance. So should have a security to be provided, and that is done through some of the operating system component, and security can be provided by making sure that only valid user can operate with that, so access control is required. And finally, when we want to interact with multiple people, multiple systems, then there needs some networking, and we need to have some standards for networking, and how all that is done is taken care by the component called networking. So let's get more insight of this by just connecting to our real-time example. That's a restaurant. So restaurant, we have multiple customers and multiple waiters, multiple chefs. So overall, lot of parallel things are being done. But at any given time, the number of tables are limited, the number of waiters are limited, the number of chefs are limited, and the number of resources like stores and all are limited. So to make sure that everything is done correctly, so we would like to make sure that everything is scheduled, and they run according to some schedule, and that way it ensures that every order is taken up, and as early as possible each order has to be completed and sent to the table of the user. So this whole process is too complicated, and unless until we have some proper management, it is not possible to ensure the smooth functioning of any restaurant. Otherwise, it gets into chaos. So we need something called a process management in the restaurant, wherein the tables are under control of some waiters, and kitchen is under control of the chefs. Each chef is allocated with a different type of preparations. So whenever a customer gives an order, then the waiter gets the order and transfers to the kitchen. At the kitchen, if the chef is free, the immediate process will start. If the chef is not free, then this order has to wait till the appropriate chef is free and all that. So that's what happens in a restaurant. And when it comes to our computer system, then whenever a new program is being executed, so we try to execute a new program. That means we create a new process. So this new process is started, and it is ready to be executed, because we are having limited resources like the processors. So whenever processor becomes free, our process starts running, and if the process requires some resources that are immediately not available, or is trying to do some other work depending on some other resource, then it can be made to wait so that other process can be taken up. So whichever process is ready to be executed, so that will go and gets the CPU's time. If any process is unable to continue, then it gets into wait state, and whenever it is again clear to continue processing, then it goes into ready state. And so this whole thing continues, and when the process completes its execution, then it will be terminated. So this whole activities are taken care by the process management, and the one which is running is decided by some other subsystem called scheduling, because multiple processes may be ready. So when it comes to multiple processes want to use the same CPU, then some sharing has to be done, some uh, alignment has to be done, or some scheduling has to be done. So there are many issues to be looked into, what we call process management. So that's where we begin our journey in the operating system, where we talk about process and its management, scheduling. and all that. So next comes there are limited resources available in the kitchen. So these resources have to be shared, and if uh, a particular item is to be prepared, and if that item requires a particular utensil, and if that particular utensil is single in number, and if it is already being used by another chef, then the chef who is trying to prepare a current item needs to wait till that vessel or the tool is made available. So these are the issues we come across because we are interested in the memory. So the various uh, processes we want to run simultaneously. So it depends on the number of stores we have. If we have only three stores, then anytime maximum three items can be prepared. But if we want to prepare more than three, then there has to be a queue and it has to be scheduled or something. So that's what happens in a restaurant where the resources are limited in number. And same thing is true when it comes to the limited memory we have. So we have a memory, it is the primary memory, which is on the motherboard. One part of the memory is occupied by the operating system, and some part of the memory will be occupied by the code of each program. So the uh, code which is in the form of a file in the secondary memory, then it is called a program. And when that comes for execution, comes onto the main memory, then we call it a process. So we have some space available in the memory to have the processes. So in this case, we are working with three processes simultaneously. So we have reserved three memory spaces for each of these processes and some more empty spaces available. That means we are still able to allocate some more processes if we want to execute. So that's how the main memory can be allocated for various processes. And if the memory gets full, then we need to do something. So we need to allocate the memory for each process, and how the memory is allocated, which process will be given which memory and how much memory, and all that is the issue to be discussed in what we call memory management in the operating system. Next comes about the file management. In our restaurant version, if you look at it, there are recipes available, there are the ingredients available. So you want to make use of the recipes and ingredients and all that. So they are limited in number, so we have to get them and then start our work. So getting into the computer world, operating system world, then the files are stored into the secondary memory, and the secondary memory is divided into some smaller chunks, and we may use continuous chunks for storing a file, or we may use uh, non-contiguous as shown here. Linked list format can be used for that. So this whole uh, system which says where a particular file is stored and which all components are there in the that particular file. So first component is where, second is where, third is where, fourth is where, and all that. So we just store under a directory system file name and where it starts and where it ends. So it starts from some location 9, and from 9 it goes to 16, from 16 goes to 1, from 1 goes to 10, from 10 goes to 25, and that is the end of it. So that's what it is trying to say. So we make use of linked list format and try to say that this is the component where we are storing the data, and one component where we are storing where the next data is stored, the link is provided on that. So this whole thing is hidden from the user, doesn't know where which part of the memory is being used for storing a particular file. Say if I try to save one mp3 file, I don't know where exactly it is stored in the memory, but yes, I know that whenever I want, I just call it and I can listen to the song. but doesn't make any sense to understand how it is stored into the memory, where it is stored, and all that is not my headache, not the user's headache. It is taken care by the operating system under the file management system. Then we have something called device management. So there are many devices being used. So we need to make sure that each of the devices are working correctly. So each device has its own way of functioning. So our operating system should know how each one is functioning, and accordingly, it should interact with each of these devices and make sure that the user can interact with the system more efficiently. The user interface, it's the interface between the user, that is a customer, and say the kitchen. So here the waiter presents a menu to the customers, and the customer go through the menu and then gives an order, and this order is forwarded to the kitchen, to the appropriate chef and all that. So this activity where the customer need not know where the kitchen is, need not know who is preparing what. He just needs to know what all items are available in that restaurant, and if wants to have that item, just places an order with the waiter, and the waiter note down all the orders and forwards to the kitchen. So that's user interface we are talking of. So we don't have to worry about how the item is prepared, how many stores are there, how many, what type of utensil is used. None of the customer's business. Only name of the item, and the quantity is what important for the customer. Doesn't have to understand what all are there and who is preparing, how is preparing, all that. So not none of the customers headache. It's just look at the menu, interact with the waiter. Waiter will get the information to the kitchen, and then from the kitchen gets back the response in the form of the dishes. The same thing happens with the interfaces. So if the system wants to interact with mouse, keyboard, or any other IO devices, then each one has got its own way of functioning. Then the operating system should have proper interface between each of these. Then comes security and access. So it is very common board we find in any hotel. That's the kitchen. Usually the customers are not allowed into the kitchen. They say no entry. So usually we have such thing like restricted area, only duty kitchen staff will be allowed inside and all that. So to ensure that hygiene, safety and all that are maintained, so you don't allow everyone to get in, and make sure that nothing goes wrong, everything runs smoothly. So to ensure that nothing goes wrong, we need to provide proper security, and we need to have proper access control, that only some type of people are allowed to enter and all others are not allowed to enter and all that. So the same way, our computer system will also have security and access controls, or different access controls we do have, and we see how a system can be secured from the outsiders, secured from the one who create problems, or secured from the virus attacks and all that, bugs, virus attacks and all that, and make sure that only the one who has proper access is only allowed to access the resources and all that. So proper access control has to be ensured, and that all is taken care by the component of an operating system. Then we find that today most of the things are working online. So from the customer don't have to go to the restaurant to have a food, so he can just order online. So the customer order goes to the restaurant online. There the order is accepted. Then it is created and delivered to the customer, and payment is made, and so on. So this whole activity is done remotely. So for such things, we need a proper networking, and this networking ensures that anywhere the customer can order and get the item from any of the restaurants. The same way, systems are interconnected through the internet or any other such networking systems, and this whole networking has to be uh, secure, efficient, and safe. So all these issues related with networking, how the different components of the internet are communicating, what are the protocols for communication, and how to ensure security, how to ensure access control. All these issues are taken care by the networking component of the operating system. So, friends, welcome to the fascinating world of this operating system. That was an intro to what operating system would be. So, the next episode of the series, we start working with different concepts of operating system. So, let's understand the operating systems in depth. So, to ensure that we understand thoroughly, we take up one concept at a time. So, thank you. Hope you enjoy this journey with me understanding the operating system concepts. So, keep watching if you find it interesting. So, please like and subscribe, and any additional things are required. So, please do write into the comments, and please share the information with your friends. Thank you. Hi friends, welcome to this series, Understanding Operating Systems, one concept at a time. To ensure that the topics about the operating system are all covered, we just follow the syllabus for second year computer science, information science, CIML students under Karnataka's VTU, just as a reference. So let's dive into the operating system concepts. I am Sandeep, working as a Dean R&D professor in ISC department in Sri Krishna Institute of Technology, Bengaluru, welcoming you to this series. So let's begin our first episode, get into what operating system is, just an introduction to that. An operating system is a fundamental software that manages computer hardware and software resources. It's an interface between the user and the computer hardware. It provides essential services like memory management, file management, and process management, etc. So the image shows here that the hardware we have at the bottom, and on the top we have a user. When the computing system began, it began in the laboratory of electronics, and it started with something digital electronics, gates, then next versions like multiplexers, adders, subtractors, decoders, and then we went on and created something called a processor. A processor works at a digital level, that means works in binary system. It understands a language of only zeros and ones. And if we want to make our system work for us, then we have to go down to its level and make it work in, and we need to communicate with the processor in zeros and ones, and that is almost impossible with the next generation of processors. At 8085 level, it was somewhat possible to work at assembly level, but later on, it's almost impossible to work even at assembly level. We need a high level versions. So the user started working with high level versions for the applications, and these applications are built to make some actions possible. But these applications are also built at a higher abstraction and to make sure that the applications interact with the hardware the proper way in spite of high abstraction. What we require is one middle layer which we call an operating system. It's an interface between the user and the computer hardware. So user no longer needs to understand what the hardware is, what the hardware features are, what the hardware can do, and all details. They can be hidden from the user, and this hiding is done through a layer called operating systems. So, what the operating system can do, just look at the list of the various functionalities performed by the operating system. It takes care of what we call process management. The code what we write is called a program as long as it is there in the backend, that is a secondary memory. But once it becomes active, then the same program comes onto the main memory and that will become a process. So which program has to come to the main memory, which program should run at any given time, or which process should run at any given time, and all that are taken care by the component called process management. Then we have a memory. That's mainly we are dealing here with the primary memory or the memory which is there on the motherboard, which we often call RAM. So it's a faster memory compared to the secondary memory, the which is of a bigger size but a slower one. So coming to the memory management, it deals with the limited memory we have on the motherboard, the RAM, and we would like to make sure that this limited memory is most effectively utilized for multi-process environment and all that. So how the memory can be efficiently utilized is taken care by the component memory management. Then a large amount of data and programs we need to store, which is not possible to be stored on the primary memory, which basically is a volatile one. We need some non-volatile memory of large size. So it may be a hard disk or a similar one. So how the programs or the data are stored on the hard disk, they are stored in the form of files, and how they are stored so that the storage is done efficiently. Nothing is wasted there. At the same time, we will be able to store and retrieve those files more effectively, the faster rate. So all these activities are taken care by the component storage management. Yes, anyway, we talk of security and protection is one of the key issues to be taken care. So when a program or the data of one user has on the memory, maybe primary memory or the secondary memory, we must ensure that others, maybe other process on the main memory or other users should not misuse the data. So for that, some sort of security and protection is required, and that is taken care by the component of the operating system, which we call the security and protection management. Once we are working on the recent systems, then we are connecting many devices to our system. It may be a keyboard, it may be a mouse, it may be any other devices. Now we are making the mobile phones connected to the systems, so many things. So to make sure that all the devices are working in sync with the system and without any malfunctioning, everything should work smoothly. So to ensure that there is a component device management, then to make sure that the user has got a easy access with the system with a minimum headache. So to ensure that easier access to the user is made available. So there was one time when everything was done with connecting wires directly onto the chips. But later we have motherboard, we have keyboard, mouse, and all that displays. So these are added for making the human activity simpler, so that human can concentrate more on building higher versions of the system than wasting time on basic activities like connecting, typing, and all that. So uh, with time, the human and computer interaction is becoming more and more sophisticated, and for that we need better user interface management, and that's taken care by this uh, part of the operating system. Then finally we have multiple systems connected with each other. So we have a network of systems, and how we ensure that this whole network of the systems work as one unit. So we need the operating system to have some features that will help in managing these all activities of interconnecting the network and all that. Yeah, of course, looks very vague if we just keep talking in a computer language. So let's come down and see what exactly we wanted to tell as an example. So let's take the old example we had in our introduction session. That's a restaurant example. So the central column is talking about the various operating system functions. The left one talks about the analogies which holds for any restaurant, and the right side column talks about the actual things we are going to study in the coming sessions of this series. So we begin with process management. When we say process management in our restaurant version, it is trying to manage all the cooking orders at the kitchen simultaneously. When multiple orders come to the kitchen, how they are managed, because we have limited resources, we have limited resources, and with that limited resources we should be able to make sure that all the orders are taken care. So on other side, in our computer version, it is like multiple processes are running on a single processor environment. Then at any given time, only one process should be active, so the processor will work on it, and all other processes should be inactive. So how to keep one process active and others inactive, and once one process changes its state from active to inactive, then who else should become active next? So that's the scheduling and all that. So many issues are related with working with a multi-process environment. It may be a single processor or multiple processors, parallel computing. Many issues are involved in that. So all the issues related with the process and how to manage them, it all is part of the process management of operating system. The second part is about the memory management. So looking at the restaurant side, there are limited stores available. If you move out, there are limited tables available. So how do you manage all this and still make sure that each of the customer is serviced in a earliest, and make each customer happy, satisfied, and all that. So we have limited resources and how to make sure that with the limited resources, all activities are taken up. So in our computer world, we have limited size of the RAM and make sure that the limited size of the RAM should be made available to all the programs that want to become a process and somehow manage the show and make sure that none of the users are able to understand that inside so much of activities are going on. So each user will be thinking that the whole memory is available to the user himself or herself. That's how a illusion is created. Same way in the process management also, the whole system is available to my program only. That's how I, as a user, understand it. So this whole illusion is created by the operating system under the memory management. Then we have file management. It's in the case of restaurant, it's organizing the recipe books and the ingredients and orders. So where do you keep them so that it is easy to identify or easy to search the books or the ingredients at the earliest so that the whole activity will not stop for anything which is missing or difficult in searching and all that. So this whole thing is what we do in this restaurant system. But in our computer world, we do have files, and these files are organized under various folders inside the disk. So this folder file or this organization, everything what is an illusion to the human, but in reality, what actually happens inside a system, it's very well managed by what we call file system. Then we have device management under the restaurant version. It is coordinating the waiters, ovens, dishwashers, and tables and all that. So making the whole system work in sync so that a whole activity is done more efficiently in a very well way. So in our computing world, it's input output devices like keyboard, mouse, the monitor, and other devices being connected to our system. So how do they manage how the interaction takes place, what language they use to interact? Yeah, this all things are created through some protocols, and these protocols will ensure that everything works smoothly. So that's the component of device management. Then we have a user interface like interacting with the customer in the restaurant. The waiters, the menus will help the customer to know what dishes are available and interacting with the waiter, the customers can understand the various dishes available, their quality, their taste, and all that. So menu will help that. So without a menu and without discussion with waiter, it becomes impossible for any customer to give an order. So we need a well documented menu, and then there should be a proper guidance from the waiter. Only then the whole restaurant system will work smoothly, customer will be satisfied, and that way. So that's a user interface, and in our computing world, we can have the graphic user interface or other systems so that human can interact with a machine. So it may be graphic user. That means we can make use of mouse and touch screen and all that, or even we can make use of the keyboard and type all the commands. So command line interface. That's the user interface. Then looking about the security and access. Getting into the restaurant, in the kitchen only chefs are allowed. others are not allowed, so that others don't go in and disturb the environment. They don't create any problems, so they don't mix anything with the dishes and all that. So the security is very much important there. So that means the quality of the food has to be well maintained. So in order to have that, only thing is only a proper well-trained chef has to attend for any given item, not others to interact or others to interfere and all that. So this security access and all that have to be taken care. On the other side, when customer is given with a bill, so it should be made visible only to the customer, not should not be put it on the notice board like thing. So it should make sure that access is only to the customer or the one who is supposed to pay the bill, not to anyone else and all that. So on the computer world, so we want to prevent unauthorized access of any of the resources, maybe files, maybe process or anything. So to ensure that unauthorized access is not allowed, proper security measures have to be taken. So authentication and all that are required for access control and all that. So that is taken care by the component security and access of the operating system. And finally, coming to the networking part of the operating system, in the restaurant version, we can talk about online orders. Then we are taking care about the supply chain, getting the orders, and then purchasing the raw materials, and then delivering the prepared items to the remote customers and all that. So these all are taken care by the networking, so supply chain. So in our computer world, supply chain activity is taken care by the internet and interconnections of the systems. So we need some part of operating system that manages this internet or data connections and provide proper protocols, proper languages to speak with one another and all that. So that's some analogy about our operating system. If we look at our common experience, then I can quote a restaurant example and try to connect the various functionalities of the operating system with what happens at a restaurant. So that's all about this various components of the operating systems and its equivalent analogy in a restaurant. So from next session onwards, we jump into various activities, various details about the operating systems, and please keep watching. And if you feel that the sessions are of any use, please don't forget to like and press the bell button, subscribe the channel. Thank you. So today we just look at what a computer system is made up of. Let's just check the organization of a computer system. So computer system contains many components, as you can see in the figure. So it mainly consists of a processing unit, central processing unit (CPU), and then it is connected to various components like memory, and the memory can be read-only memory ROM or random access memory RAM. Both of them are put on the motherboard, and at the back end where we have secondary memory, for that we will have various disks. So it's a hard disk and other disk like compact disk, CD, and all such things. So for uh, having proper interaction with the disks, we have something called a disk controller. Then to make sure that the human interacts with the machine more efficiently with minimum troubles. So many I/O devices are attached to the system, and to ensure that all the I/O devices work more efficiently, then we have controller for I/O devices. The I/O devices may be a keyboard, monitor, display, printer, and many more. Now the question is how they are interconnected. So on the motherboard, mainly we find three types of units. One, the central processing unit, and the second one is the memory, and the third one is the one which is connected to the outside world through I/O. Now the CPU has to interact with the memory and various devices, and for that we make use of a bus system. And in the bus system, mainly on the motherboard, there are three types of buses we have. One, the data bus, which is used to transfer data from one unit to another unit, and then there is an address bus, which identifies which of the devices is to be used. So the address will tell which device to use, and in that device where or which part of the device to be used. Or if you are talking about memory, then the location of the memory is represented by the address. So part of the address decides which device we are working with, and other part of the address talks about the internal locations. So overall, the address bus is going to define which part of the system or which part of the component is being interacted with the CPU. And finally, we have something called control bus, and this control bus is used to decide what type of activity is going on. Is it the processor wants to write onto the memory or wants to read from the memory? And if it is wants to write to memory, in what format it wants to write? If it is trying to read, in what format it is trying to read? If it is trying to read from the keyboard or trying to read from the mouse, or if it is giving instruction to the printer, all these are controlled by the control bus. So if we are trying to uh, write some data onto the memory, then what data we want to write onto the memory, that data we put it on the data bus. Then we decide where we want to write it on the memory, the location where the data has to be written. So the address, so made up of two components. First component talking about which uh, device is to be used, and the location in that device. So these two together form the address, and this address is put on the address bus, and then finally control bus will initiate which action to be taken. So here we are trying to write onto the memory. So CPU puts data onto the data bus. CPU tells where to write. So put the address onto the address bus. And finally CPU says that the activity to be done is to write. So the write message is created onto the control bus, and because address bus contains address of the memory, so appropriate memory gets ready for the action. Data is ready on the data bus, and finally control bus will give a control signal that whatever is there on the data bus should be written onto the memory, and the memory component knows where to write through the address bus. Same way, if we are talking about reading the keyboard, then first thing is address bus will inform that we want to interact with the keyboard. So the address of the keyboard is put on the address bus, and then control bus says that it is a read action. So the keyboard is active because of the address bus, and read action is initiated by the control bus, and when any key is pressed, the details of the key pressed gets into the database, and through the database, controller understands that what is being typed. So if CPU wants to know what key is being pressed, then it has to first enable the keyboard, giving a address of the keyboard, and then giving appropriate control signal to enable the keyboard, and then finally wait for a key to be pressed. And when a key is pressed, then the data bus gets the data, and IO device like that keyboard will send a control signal saying that one key is being pressed and the data is put on the data bus. So this information goes to the CPU. Until then, CPU will be waiting for some key to be pressed. The moment a key is pressed, the IO device or the keyboard will send back a control signal saying that a key is pressed and the data is on the data bus. So CPU is now free to read the data from the keyboard. So these all activities take when we are working with the IO devices with the memory, and how CPU interacts with the memory and various IO devices. And for making all these things possible, one option is if we are looking for keyboard to read. So there is a lot of speed disparity. The processor is working in nanosecond speed, and the one who is operating with the keyboard, a human, is working with a response time of best case is in terms of milliseconds, even if he types the fastest way. Then between two keystrokes, we will have some milliseconds of delays. And these milliseconds of delays, when you compare with the processor's speed, which is working in nanosecond, so it will be millions of cycles of the processor. It has to wait between two keys, and how this can be improved instead of making the processor wait for keys to be pressed. So what we can do is we just tell the keyboard just to inform me whenever a key is pressed. So instead of keeping the keyboard ready for working as we did in the previous discussion. Now what we can do is, instead of making CPU wait for keyboard, we just give an instruction to keyboard that whenever any key is pressed, you just tell me. So what should I do then? What should CPU do then? So let the CPU continue working whatever task is available for that CPU to do. So millions of time frame is available between two keystrokes, and that millions of cycles of the CPU can be used for some other execution, some other activity. So what we can do now is let the CPU continue working with its current activity, and in the background let the keyboard be waiting for the human to press the key, and anytime a human presses the key, we want the CPU to know that this key is being pressed, and if that pressing of the key makes any sense to the CPU, then CPU should take appropriate action and all that. But how to make CPU to know that a key is pressed? So there comes what we call an interrupt. So interrupt is a process where these slower devices and all that can interrupt the CPU whenever some special event happens, like a key is pressed. So whenever a key is pressed, the CPU gets interrupted and says that a key is pressed. And if pressing of that key means something to the CPU for a given process, then it takes a corresponding action on that. And if it doesn't make any sense, then it just neglects the pressing of the key and so on. So for example, if just a window screen is on and you try to press some keys, it may not make any changes in the system, but same thing when the screen is open with some Word document, and in the Word document is in edit mode, then whatever key you press, it gets displayed, and for that what is required is the CPU should know what key is pressed, and then it should inform the display system to display a particular character at a prompt and all that. So this activity takes place when we are working with slow devices and all that. The same thing is possible with other things. So interrupt is mainly used to interrupt whatever process is going on, whatever CPU is currently doing, and we just try to interrupt it to make some special events to occur. So whenever we want some special events to occur, we try to interrupt the CPU, and the CPU will decide if that special event is really special in the current situation. If so, it will do some special actions. Otherwise, it may just neglect and continue whatever it is doing. So looking at the figure, we can see that the interrupts can be of two types: the hardware interrupt, software interrupt. So the hardware interrupt, as just discussed, it is coming from a hardware like a keyboard, mouse, or and all that. So if I just move the mouse, my this icon is moving, the pointer is moving. So to make sure that the pointer moves, the whenever the mouse is moved, then a message goes to the CPU saying that mouse has moved, and the CPU should respond if required and make the position of the mouse change as per the instruction getting from the mouse and so on. So that's what we call hardware interrupts. There are two types of hardware interrupts. One is coming from the external like IO interrupts, like coming from the keyboard or the mouse and all that. And there is another interrupt which is internal interrupt. That is something like exceptions. When you are trying to work with some address and all that which is not allowed, then exception is raised, and because of that, the computer or the CPU has to stop execution. So that is also comes under the hardware, and that's external. Yes, just as discussed, keyboard, mouse, and all that are the hardware components that are basically working very slow because it's mainly human related actions, and human reaction time is in milliseconds, and computers working is in nanoseconds. So there is a lot of disparity between the two speeds, and not to waste the precious time of the CPU, let's allow CPU to continue working, and whenever input from the human is available, let us interrupt the CPU and make it work for a special purpose and all that. On the other side, there are something called software interrupts. They are generated by the program. So here, program generates user-defined programs, and user-defined interrupts are there. And these are useful whenever we are calling a system calls. So system calls, whenever being called, we have to stop the execution of whatever currently we are doing, and then make some changes like required while writing device drivers and all that. So basically, the interrupt is used to signal some event being uh, if a particular event occurs, we want to make a CPU to be aware that such an event happened. So to inform the CPU, we do have something called interrupts. They are of two types: software, hardware interrupts, and these are the signals for event handling. So that's all about the system organization as of now, and many more issues to be discussed. So let's get to the another concept in the next session. So till then, take care. Bye. Hi friends, continuing our discussion of the operating systems. Now let us see the need of a bus system while connecting the various components of a computing system with the CPU. The need for bus system arises because the number of pins available on any CPU is finite in number or limited in number, whereas we require unlimited number of connections to be done, as we discussed in the previous session. So any uh, say memory, any element in the memory can be identified through an address, and then the data can be collected. So for every interaction between CPU and any component like memory or any IO device, we do require three connections, one for identifying the address, and one for the data transfer, and one for controlling what type of action to take place. Is it a read action, write action, and so on. So synchronizing with time, what actions to be taken and all that. So address, data, and control lines are required to be connected from every CPU to each of the components in the system. So to make sure that each one can be connected individually, then you can imagine how many pins are required. Say, for example, if we are talking about a 64-bit processor, it means that it can any given time take input of 64 bits or give an output of 64 bits. So it interacts with neighbors with an data of 64 bits at any given time. So if each of the device wants to interact with that, then between CPU and each of the device, we do require 64 bits or 64 lines of connection. Say if there are thousands of various components in the computing system, then thousands of 64 lines need to be connected to the CPU, and that makes it impossible for making a chip with thousands of 64 pins available. This is only for the data component. Same way, if we talk about address component or talk about control component, then each one has to be separately done. Then the number of connections, the number of pins required on the processor chip grows exponentially large, which is impossible to work with. And another important thing what we see, or a relaxation for this problem comes when we know that only one processor is there, and one processor can interact with one of the components at any given time. It cannot interact with all the components simultaneously because there is only one processor to work with. So since there is only one processor to work with, then there is no point in having a separate connection for data connection for memory, separate control connection for memory, separate address connection from memory, separate read write connections to the memory, and on the other end, if we are reading from the memory, then separate data connection back to the processor. In same way with each of the IO devices, we don't need a separate address, separate data connections to be done. So it saves a lot because at any given time, only one of the components and one of the operations pertaining to that component is uh, possible to be used, only that can be used. Therefore, there is no point in having all wires connected to each one. So instead of that, we can go for what we call a bus architecture, where all the elements are connected in parallel. All the elements are connected in parallel, and whichever component the CPU wants to communicate with, so through the address line, only that particular component is made live, and all other components will be in sleep mode. So only one component that is required for communication will be kept alive, and all other things will be in off state. And this way, the address bus will allow only one of the components to be active and all other things to remain inactive. Then the control bus will tell to read or write. So because only one element is active because of the address bus, so whatever signal is given to the control bus is read by only that particular component which is alive, and all other things are in sleep mode, and hence they cannot respond to whatever control signal is coming. And the data is connected only to the component which is live at any given time. So through this arrangement, we can reduce lot of redundancy, lot of extra wiring and all that, and that definitely simplifies the design. So we know that any given time, only one of the components is going to communicate with CPU, because there is only one CPU that can communicate with the neighbors. So the CPU has to communicate with the neighbors, and one CPU means any one of them should be communicating. Therefore, no point in connecting each components individually separately to the CPU. So we can make all the connections in parallel and keep only one element active and all other to keep inactive. So this is done through enable and disable uh, activity, and this address bus will enable a particular component, and then the control bus will guide whether to write or read or whatever activity. And because all the components, only one component is active, all the activities are done by that particular component, and hence the designing becomes simple. So we are going to save a lot of connections, therefore it is going to be highly cost effective and scalable. So when you want to add any new device, just connect to this bus in parallel. So three connections need to be added to this bus for every element. So for every component, three connections have to be done to this common bus, one for address, one for data, and one for control. So it becomes quite easy for changing the size. So adding more devices doesn't need to change any uh, design. So just it becomes simple to scale and highly flexible. So anytime anything can be inserted into the system, anytime anything can be removed from the system. So it becomes highly scale flexible, and we make use of efficient use of the resources is possible through the bus system. So that's why we go for bus configuration while creating the connectivity. So when you are organizing a computer system, so we have many components, and all the components can be connected in parallel through the bus arrangements, and this will simplify the design. It becomes cost effective, it is highly scalable, more flexible, and efficient use of resources is made possible. All this is made possible only for one reason, because one CPU any given time can communicate with only one device. One at a time is possible. Therefore, there is no point in connecting each one individually and making the whole system too complicated and making it messy. So that's why we do go for a bus system, and many more issues to discuss in this series. So keep watching. Thank you. Hi friends, welcome back. In this session, let us look at the system architecture of a computer. The computer architecture is the blueprint for how a computer is designed and built. It defines the structure and behavior of a computer system. It encompasses the hardware, software components, and communication between them. So we have different types of architectures possible. So the simplest one is a single processor architecture where we have one CPU, and this one CPU is connected to all the peripherals through the bus as discussed in the previous session. So we have bus arrangement where all the peripherals are interacting with the processor. Processor in turn consists of many elements like arithmetic logic unit, memory buffer unit, memory address unit, and many more such things. And also we'll have memory, which we usually call a cache memory. And because this memory is within the processor body, it is very well designed and will be working at a processor speed. Whereas other memory, what we call, it's the primary memory, which is on the motherboard. The motherboard will not be working at the processor speed, will have many problems. So it will be working quite slower than the processor. So for example, if the processor is working at nanosecond speed, then the memory will be working at a microsecond speed. So somewhere 1,000 times slower because the design of the processor, the environment in which a processor is designed is quite different from the environment where the motherboard is designed. So the speed of the motherboard will be quite low compared to the processor speed. So the primary memory will be working at a far slower compared to the processor. And since cache memory is built within the processor environment, it will be working at a almost processor speed. And we have I/O devices also connected to the bus. So I/O devices through their device drivers are connected to the system via the bus. So that's how the single processor environment would look like. So we have one processor connected to its cache. Then we have bus, and to the bus main memory and the I/O devices are in turn connected. Then we have another environment where we call it as a multiprocessor environment where we have multiple CPUs, and as we can see in the figure, so there are multiple processors, processor 1, 2, 3 up to N, and each processor in turn has its own cache memory, which we call L1 cache. So each one has its own cache memory, and along with that, there is one more memory which is provided to individual processors separately. So if processor 1 is working with some set of data or some process, then it will be stored in L2 cache. Same way, processor 2's L2 cache will be storing the process 2's data and process details and all that, and so on. And what is common to all them will be stored in this common memory, which we call a shared memory. So when we are working with a large amount of processes, then we would like to make a parallel processing possible, and this is what we would like to work with. So this is possible because of the technology being enriched, and because the technology is improving, the size of the circuitry is getting reduced, the space required for building the circuit is reduced. But to ensure that the chip is usable by the humans, it should have some physical size. So to maintain that physical size, then we realize that a lot of the space is available free inside. So in order to make use of that, instead of leaving that space free, we can build new processors on the remaining space, and with that what we can have is on same chip we'll have multiple processors. So that's one aspect. On the other aspect was with the time we have seen that the processor speed went on increasing from megahertz to gigahertz. But later we realized that at 3 gigahertz and above, the processor started becoming very hot and all that. So there were other problems associated with the chip designing. Beyond 3 gigahertz, it was not possible to go for increasing the speed. So we had to stop the speed to somewhere 3 gigahertz. But luckily, the size was shrinking and hence more space was made available in the physical chip. And instead of having one CPU, we started thinking of multiple CPUs in that, which we started calling core. So at the beginning, it was a single core. Now it went on to dual core, quad core, and so on. So it is just a N core chip we are talking with. So this is a N core chip we are talking where there are N processors inside, and each processor is associated with its own L1 cache and its own L2 cache, and that is in turn connected through the bus to the outside world like shared memory and other IO devices and all that. So the advantage of this is when we are working with multiple processors and we can allot one processor to each process and all of them can be run parallelly. In case of single processor environment, even though we were trying to work on multi-process system, but only thing is that there was time sharing and any given time only one process was working and all others were in sleep mode. But because they were working at a very high speed compared to human perception, we could feel that all are working parallelly. But in reality, they were not working in parallel. Only one process was active, all others were inactive in the single CPU environment. But now with multiprocessor environment, if there are n processors inside a chip, then we can allot one chip, one core for each process, and hence all n processors can be used parallelly to work with n processes. And this at the beginning, each process will be got from the secondary memory to the primary memory, which in this case is the shared memory. And from the shared memory, each process gets into the cache memory. The cache memory is one which is working at a high speed. Therefore, the technological limitations are there that we cannot have any huge amount of memory as we wanted. So there is limitations for L2 cache, there is limitations for L1 cache, but shared memory which is there on the primary, so we can have a very huge amount of primary memory possible here, but the cache memories are of limited size. Therefore, uh, for each process, a part of the code will be taken into the L2 cache, part of the data is taken into L2 cache, and then it is supplied to the L1 cache, and processor is working with the L1 cache, whether it is process or data or the stack. So all these three components are put on the L1 cache, and whenever we are out of stock, then it is again taken from L2 cache, and if that is not available in L2 cache, then it will be taken for shared memory. So this all discussions we take in detail in memory management and all that. So what all happens here is we have multiple processors, multi-core processor to be precise. So we have a multi-core processor and that is connected to all the outside world through the bus, and that's how multi-processor environment works. Then the next version of that is the clustered systems where we are talking about node. So in the previous thing we said that there is a multiprocessor environment and that is a multi-core processor. So we have each multi-core processor used as a node and we have various nodes and they are interconnected and they in turn are having the common shared memory. So in each node you can see multiple CPUs and there is shared memory, and all these are again interconnected and they are made. So this stuff something like a cloud environment and all that. Then Current trend is about the multi-core chips, where we are talking about multiple cores. So we have a bus interface and then shared memory, and from that individual memory for each core. So there are multiple cores. So as we discussed in the previous few minutes back, so from the bus we have other off-chip components. So this whole thing in the violet band is the multi-core processor environment, and this the blue one, the light orange, and this red one, all these together are part of one processor, one chip, wherein we have shared memory, we have individual memory, and we have core processors. So this whole thing is one chip, and that is connected interface through the bus to the outside world. So that's something about computer system architecture. So we have different types of systems like single processor, multiprocessor, and then clustered systems. And this multiprocessor is other way we can call it a multi-core system. So in this multi-core, we can run different process for using each core, or even a single process can be divided into different parts, and if they can be run parallelly, then we can run them in parallel so that we can speed up the process. So that's all for now. More details to follow, so keep watching, and please don't forget to like and let's continue subscribe and to our next session. Thank you. And in this session, before getting deeper into the operating systems, let us first look what made the operating system come to exist. So let's see the history of the operating system. It all began in late 1970s and early 1980s, when the computing world was ruled by a variety of processors manufactured by Intel, Texas Instruments, Motorola, Zilog, AMD, and many more. So many processors were available. Each processor will have its own instruction set, will have its own architecture, will have its own I/O connectivity and all. So they don't match with one another because they were independently manufactured by various companies, and hence a lot of variety was available. Then the computing world, or the computer manufacturers, especially the one which we are today talking about, the personal computer, which in short called PC. The PC manufacturers, so they were like IBM, Compaq, Dell, HP, and so on. So they used these processors, and they organized the overall computing system, connecting the peripherals with these processors, like the random access memory, read-only memory, and other I/O devices, other memory, secondary memory, the screen, the keyboard, and all such I/O devices were added, and they each of these companies created their own computer organization, and they organized these components as per their requirement, and hence so we had a very large variety of processors, and these processors in turn were organized with the other components in a variety of ways, and hence in before the early 1970s and before that, a lot of work was tailor made. So if wanted to say connect the keyboard to the any system, then the system would be this keyboard would require one address so that when a key is pressed, the system can understand that the keyboard is sending some information, and to understand which key is pressed, then there is some protocol. So we need to define some protocol. So these all activities were tailor-made by individual who was using any system. So this during early 70s, all these for every activity, that whole thing has to be tailor made by the user. So from scratch everything has to be created, and it was a big headache, and hence there was no much development because most of the time we are only writing the elementary code, how to interact with the uh, components of the system, how to interact with the peripherals, and how to make a human to interact with the machine, and how to understand the result machine is giving and all that. So most of the time we were busy only in coding for these activities, and that was taking much of our time. Then we have something called the Department of Defense (DoD) of US government, which wanted to standardize all these activities because each time any activity has to be done, that we have to start everything from the scratch, and it was becoming a big headache. So there was no chance of getting forward. So all the time we are stuck with only the basic activity, and the DoD wanted to standardize all these actions, and it makes sense because 70% of the software market was purchased by DoD. So 70% of the software which was created then was utilized by the DoD, and it was having the say number one say on whatever software developers were to follow. So whatever DoD says, the other software developers had to follow those days because 70% of the share was by the DoD. And the DoD was using IBM computers, and IBM computers in turn was using Intel processors, and that link made the whole evolution, revolution, whatever we call. So the whole scenario is early 70s. There were many processors, many organizations of these systems, and for each of these, any software required was built by the user as a tailor-made softwares. And when DoD thought of standardizing this, because interoperability and the one software written by one can be easily used by someone else, and that is only possible when there are some standards, and if we everyone follows that particular standard, then interoperability, exchange of the information, exchange of the tools, exchange of the code, everything is possible. And the another reason why software world has to bow down to DoD is it's a 70% market share, and because DoD is 70% of the software purchaser, so every software would like to oblige with what DoD says, and DoD was using IBM computers, IBM computer in turn was using Intel processor, and through this, what happened is IBM format, Intel, IBM's organization, and Intel's architecture, Intel's instruction set, Intel's other pin diagrams, and all that's become a standard. And this time, Microsoft grabbed the opportunity instead of having these individual codes separately. So if you want to use a keyboard, we use the software. If we want to use display 7 segment display or something, we need a code. If we want to put it on the dot matrix display, we need a code. If we want to get it printed, we need a code. And that way we just need one code for every activity. And these codes were written for Intel processor, using Intel processors instruction set, and using the IBM computers organization. So these all were taken and compiled all these functionalities together, and came out with something called disk operating system. And this very famously known as MS-DOS, because MS stands for Microsoft, and DOS, DOS, disk operating system. So this is the, you can say, commercially first software available for any PC to use. So Microsoft conquered the world through compiling all the functionalities available to work with. And they wanted to target the major market, and the major market is Department of Defense, and Department of Defense used IBM computers. So Microsoft targeted the IBM organization of the system, and then IBM in turn was using Intel processor. Therefore, Microsoft targeted the instruction set of the Intel processor, and that way the whole DOS disk operating system came into existence. And because of this, the next revolution started was everybody wanted to be with the standard, because once I come to know that all these standards are available, it's no point in creating all these tools again from the scratch. So why not use the readily available tool, which is MS-DOS? So everybody wanted to use MS-DOS because it is available. So we don't have to scratch our head and create all the tools for interacting with our peripherals and all that. So the problem there is they wanted IBM type of system, and in turn they want a Intel processor and all that. So this created a problem to other companies like the Compaq, Dell, and other companies who were using other processors like manufactured by Texas Instruments or Motorola or Zilog or AMD and all other processors. So to keep themselves alive in the market, the other companies just cloned the IBM architecture and the organization. So IBM organization means the central processing unit is some Intel processor, and then the motherboard is created such that the IO devices have a similar addresses and all that, similar functionalities for each IO devices to be used. And that gave birth to a new term called IBM compatible. In 1980s and 90s, this term was very much famous, very much common, and anybody wanted to purchase a personal computer, first they would ask for IBM computer. Because if I go for IBM computer, then I can just make use of the MS-DOS, and I don't have to waste my time in creating all these tools myself. I don't have to tailor make any of these tools. Therefore, I just would like to purchase IBM computer. But then other computer market just dropped down. So they came out with this idea that they created one translator, a translating layer between the hardware and the outside world. So inside the hardware, they have their own system. So it may be a Dell system or it may be any other one, and which in turn may be using a TI processor or Motorola processor or Zilog processor or whatever it is. But there was one translator. So the user used to talk in MS-DOS language, and MS-DOS language is converted to the native language of the hardware, and the hardware understands its own language and performs all the operations required and gives back the answer. But the answer given was in its own native language, which is linked to the user, and hence it is retranslated back to the MS-DOS language and comes out. So this translation from DOS to the native and native back to the DOS was implemented, and that's what we just call it cloning IBM architecture and organization. And then they started selling their systems with a label called IBM compatible, and they started claiming that whatever IBM computer can do, our system also can do. So you can happily use the MS DOS for your operations on our system. So that way, the IBM become a standard, and because of IBM, Intel became a standard those days. So now new things have come up again, and there are a lot of technology changes and all. But the first revolution of personal computers happened in late 70s and early 80s, and this is what the story is all about. How operating system came to existence. So, and because of all this, the operating system was born. Till then, there was nothing like operating system. Each one was doing their own tailor-made softwares. But once this whole thing was compiled by the Microsoft, and MS-DOS was created, then a operating system was born. Yeah, rest is the history. Then the DOS was there, the various versions of the DOS were there, then Windows came and continued. So we are not here into discussing about all different versions of the DOS and all that. But yes, we are just trying to see how the term operating system was tossed and why, and what was the need for all this. It just began by the R&D team of Department of Defense, US government, who wanted to standardize this whole thing. So their work gave birth to this all. So we are whatever systems we are using, it's all because of the origin which happened in the Department of Defense through IBM computer, through Intel processor, and then all that. So that's a history of operating system. And then let's keep looking at the various details about operating systems in the coming sessions. So keep watching. Please don't forget to like and subscribe the channel, and hit the bell icon so that you get whenever a new episode is published. Next usual, where we look at how an operating system is structured. So the structure of an operating system is the blueprint of the operating system, how an operating system is organized and how the components are interacting with each other. So the whole blueprint is put, and that is what we call a structure. So to begin with, the early version of the operating system was very crude, and it was working for a single processor, and the process was a single process at any given time. So any one process it used to work on, and that was a simple operating system structure where we began our journey. So as discussed in our previous video, the history of the operating system, or how the whole thing evolved, or how it all began. So if you look at that, it's just a simulation of all the functionalities and put together is one form. So that's all put under one basic input output system drivers. So this is a BIOS. It's usually a small bootstrap code which is written on the EEPROM or ROM. It's a read-only memory. It's a part of the motherboard, and whenever we switch on the system, it begins to execute the code from this, because by default it starts from some address location, and that address location belongs to the BIOS. And here we get the device drivers that necessary. So to begin with, the two devices are essential to work with any system. One is the keyboard and one is the monitor, because we want to give input to it and see what the system is trying to tell us. So these two have to begin with. So the basic input output device drivers are put on the BIOS, and once that is done, a small component of the operating system is put on that, and then we have other device drivers, and then the system calls and all that, and finally comes to the application program. All this here we have shown in some structural form, but in reality, the simple, the first version of that was not well structured, and then it was very small and having limited features, and the interfaces and functionality were not well separated, so it was just made as one component, the all functionalities, whatever we wanted, just combined together to make it one software called a disk operating system or something like that. The advantages of such simple software is easy in the development and gives a better performance as long as you are working with the simple problems. But the negative part of that is a lot of times the system may fail because of some malfunctioning, and it's difficult to maintain. So there is poor maintainability issues related with this. So to overcome this very crude operating system structure, we shifted to the next one, which we call a monolithic. So where what we have is one hardware, on top of that we have one kernel, and then on top of that we have application programs. The difference between this and the previous one is all the applications will be working in unprivileged mode, whereas the kernel operations are working in privileged mode. So privileged mode means they have extra say on the usage of the resources compared to the unprivileged mode. So any given time, two actions require to use any resource, one from the unprivileged and one from the privileged, then first preference will be given to the privileged mode request. Only when no privileged mode is requesting for the resource, only then unprivileged mode request will be served. Yeah, that's the advantage of the second one. Here, all the functionalities are put under one kernel. The difference between this and the previous one is there was nothing like privileged mode, unprivileged mode. Everything was in one form of thing. But here we have a privileged mode, so all the kernel activities are taken here in privileged mode. So all the operating system functionalities are defined under one kernel. So single kernel, all services are defined in this kernel space. Linux, Unix, and all are examples for such thing. The advantage is it is fast, so there is less context switching required. We'll look into detail about context switching and all that in our future sessions. Direct access between the components is there, and hence it will be useful. But the negative part of that is it is less secure, because a bug in any of these modules can crash the whole system. So if there is a problem in file system, then whole system will stop working. If there is a problem in drivers, then whole system will stop working, because everything is one unit, and anywhere or problem is there, then the whole system collapses. And the other problem is to maintain and update. It is too difficult. So if we want to have a better service, say in file systems, then just we cannot change the file system component. We have to modify the whole kernel itself. That means while changing any one component, the whole thing has to be rewritten, and in that we may again create new problems by rewriting and all that. So that's one side. we have a privilege mode here compared to the previous one, but we have a problems like any bug anywhere is going to disturb the whole system and harder to maintain or update are the two problems mainly we can see in this. So to overcome these two problems, we need to go into the another one. So before going to the next one, let us check one example where we were working with an example of a restaurant. So imagine that restaurant where only one kitchen is there, which is huge in size and handles everything. Cooking, billing, cleaning, supply ordering, everything is taken care at one place only. So it looks very fast, but definitely it is risky. If any one chef makes any mistake, then the whole kitchen may shut down. So that's a problem with what we call monolithic operating system structure. So to overcome this, we come across with another operating system structure, which we call microkernel. Instead of having a whole thing as one kernel, you just define one microkernel where all the basic things are defined under the kernel. Only the basic things are defined under the kernel, and all other things are defined separately. So the common things applicable for all the functionalities are defined under the microkernel. So only essential functions are in the kernel. That is like CPU scheduling, inter-process communication, basic memory handling, etc. The essentials and compulsorily required things only are there in the kernel now. So now the size of the kernel is small, so we call it a microkernel, and other things are defined individually as a different modules. So if you are talking about device driver, then we have a separate unit called device driver, which is link between application and the microkernel. So if there is any change in the device driver required, then only this component has to be updated without disturbing any other component. So that's the advantage of working with a microkernel. So only essential things run in the kernel space and all other things run in the user space. So user space means they are less privileged and kernel space means highly privileged. So the examples are Minix and other operating systems. The advantage is more secure and stable, easy to update, replace individual services. So we can just update any of the services individually without disturbing others. The problem is the overhead due to communication between modules. So between modules, there will be, if there are communication, then there will be a lot of overhead because earlier all these modules were part of one kernel, but now they are independent entities. Then they need to interact with each other, so there will be more overhead and interaction between the modules. And definitely because of that, the performance is little slower because the kernel mode or the more privileged mode works only for essential functions and all other functions are working at the user mode. So user mode means any kernel mode activity comes on the way, the user mode activity will be paused and the CPU is given to the kernel mode activity. So whenever any of these applications, so file server, Unix server, device driver, application, IPC, any of these are being executed and during that time if any of the kernel activity comes on the way, then this will be stopped and this will be taken up. So every time a kernel action comes, then the user actions are stopped. So that way the whole system becomes slower. So that's about the microkernel. Then we have an example for that. And here a microkernel can be taken up as a restaurant manager. He's only there to take orders and assign the tasks. So he just take the orders, cooking, billing, cleaning, delivery are handled by external teams or the user space services. Only the restaurant manager working in the kernel mode and all others are working in the user mode. If one fails, then rest can still operate safely. So if one table having a problem of cooking or billing or cleaning, other tables will be running without any problem. If one item is not properly cooked, at least other items will be cooked. So that is the advantage of working with a microkernel. So this figure depicts the difference between the what monolithic kernel and microkernel is. So we have hardware in the bottom, and then the blue one is talking about the privileged mode. So and the monolithic device driver, dispatcher, scheduler, IPC, file system calls all come under the privileged mode. Only application is in the non-privileged mode. Whereas in the microkernel, only the microkernel is in the privileged mode, all others are in the user mode, and hence any disturbance is there for freeze, then it can be stopped. Whereas all these in the other side, all these are working in kernel mode. Therefore, once they start working, they cannot be stopped on the way. Whereas in the user mode, if it is working, it can be stopped temporarily and goes down to the kernel mode and then continue that work and complete that and come back and make the user mode activity continue working. So anytime kernel mode activity comes on the way, then the user mode actions will be interrupted. So because of these interruptions, the user mode processes always will be running very slowly, and the monolithic thing, everything is in the privilege mode, therefore it will be faster. But in this case, only few of the essential facilities are in the kernel mode, therefore there is chance of a lot of interruptions, and hence this whole thing will work slowly. The next operation will be about the layered structure. Here, the operating system is built in layers. So we have one layer of the hardware, then on the other we have CPU management layer, then memory management layer, device drivers layer, IO management layers, and application layer, and so on. So in this case, the advantage of this is if any of the things have to modify, then independently we can just change each of these layers without disturbing other layers. So it is highly organized and easy to debug. So when you identify there is some problem, then you can easily identify which of the layer is responsible for that problem or for that bug, and it is easy to debug it and easy to solve the problem. Each layer can be tested and maintained independently. There is no dependency anymore. Each one can be separately tested. The disadvantage of this is less efficient due to strict layer-to-layer communication, because hardware cannot directly interact with the application, hardware cannot directly interact with the device drivers. It has to interact with the CPU management. CPU management in turn should interact with the memory management. Memory management should inform to the device driver. Device driver should inform to IO manager. IO manager only can communicate with the applications. So this is a layer to layer strict communication is there, and because of this it will be less efficient, and lower layers must be perfect, because the lower layers are directly more nearer to the hardware. If anything goes wrong on the lower layer, then the error can propagate up. So if there is a small error in the CPU management, then that error will be enlarged in the next layer. It will be further aggravated, further aggravated. By the time it reaches the application layer, the error might have gone multifold, and that becomes a problem. So that's pros and cons of layered operating system structure. So here, example can be a multi-story restaurant where each floor is having different actions, like ground floor handles all the raw materials, first floor may be processing the ingredients, the second floor cooks are there, third floor service serves the dishes. Each floor depends on the one below. So if you want ingredients, then it has to come from raw materials only. If you want to cook, then you need ingredients. If you want to serve the dishes, then it should be cooked. So the flow is the raw materials are there in the ground floor, they go to the upper floor, become ingredient, then go to the upper floor, they are cooked, then the cooked things are served. So this is how it has to go. So you can't just bypass any of that. So it's directly from ground floor. If you go to third floor, it is like we are serving the raw material without cooking and all that. So it is very highly organized, but slower than one room kitchen. So that's analogy we wanted to give. So to summarize all that, if you look at the speed, the monolithic kernel will be the fast one. Layered operating system will be moderate in the speed, but microkernel is very slow because of every time it has to message, and most of the units are working in the user mode, and hence they are it is possible that they can be interrupted on the way, and every now and then if it is getting interrupted, definitely to complete any given task it takes more time, and hence it becomes slower. Modularity, yes, microkernel is highly modular because anything can be easily replaced and modified, and layered operating system is medium. Monolithic, definitely it is very poor maintainability. It is very difficult in monolithic, very easy in microkernel, very easy in layered, because we immediately identify exactly where the problem is, and how to solve that. It's very easy in both microkernel as well as layered operating system. As far as security is concerned, the microkernel is highly secure because in this case, very few things are working under the kernel mode. Layered operating system say okay, but monolithic is highly risky because any one thing fails, then everything will fail. Here they are working in parallel, therefore if one thing fails, then others will continue. So having a better security. So looking at the example, the monolithic kernel is Unix, MS-DOS, microkernel is Linux and Mac OS, layered one is Windows NT, that's a old version and all that. So that's all about the uh, structures of operating system, various types of structures of operating system. So please do like the video. If you like this, press the like button. Please subscribe to the channel and hit the icon button so that we share the notifications whenever new video in this series comes up. So please do like it and to another session continue on watching this. Thank you. Operating systems. So in this session, let us look in detail about the operating system operations. So basically, in the modern computing system, the operating system works in dual mode, and the dual mode is basically designed to provide a layer of protection and stability to computer systems by separating the user programs and the operating system into two different modes. User programs are written by the users who are not very much specialized in writing the code, may not be experts in writing the code, so they may create some unstable code so that it may disturb the whole system. But as far as the writers or the code writers of the operating system are concerned, they are experts, and hence the chances of committing mistakes are almost zero. So all serious actions are taken to ensure that no errors pass through any security gate so that everything works perfectly. But as far as the user is concerned, a common man is concerned, or a simple programmer is concerned, we can't guarantee that. Therefore, it is better to keep the user uh, not having all the facilities to interact with the actual hardware and all the main facilities. So we can ensure security through making two modes of operating system. work, one under the user mode and one under the kernel mode. The user mode, usually the applications through which the user interacts, and these applications and the code written by the user work under the user mode of the operating system. And under this mode, the access is restricted to the core functionalities of the system so that it is not allowed to interfere the system's working. So by mistake or by any uh, harming intention, a user may write some code which may disturb the overall functioning of the system. So to ensure this security, only the user level activities are allowed to function, and these activities that are working in user mode can interact with few components like compilers, user applications, and may use system libraries using the system calls. But on the other side, we have all the hardware and the control code that is part of the operating system that is used to control the hardware that is actually using the hardware. So if we are working in this mode, then we have all the facilities, all the privileges to directly access the hardware and other system resources. Because the operating system components which are written in the kernel mode or which are allowed to work in the kernel mode have gone through a series of filtering, a series of testing and all that, so that they are 100% foolproof, and hence they are allowed to interact with the CPU, RAM, hardware, and other resources directly. Whereas if it is the user mode applications, then the hardware can be accessed only through the tasks that are working in the kernel mode. So if a user wants to compile anything, then it has to use a compiler, but the compiler is working in the user mode. And if compiler wants to compile the code, then it has to send a request. That request is called a system call, and that system call enables the kernel module, and that kernel module, if the system call is genuine and it is authenticated, then the kernel module will allow the hardware and other system resources to be used. So this way we can ensure security. So no system user defined functions can disturb our overall system. So that's way we ensure that the whole system is secured. Then there is a possibility that the user program may get into sometime infinite loop. So when any user program gets into infinite loop, so like an example, maybe the earlier initial versions, anyway, we are trying to divide, then usually the division process is done through subtraction, because at the hardware level there is no hardware available for division and multiplication. We have addition and subtraction hardware for that. Therefore if we want to multiply two numbers, then we keep adding the one number to itself by another number of times. Say if I want to multiply a with b, then a gets added a plus a b number of times, and after adding a b number of times, we get a into b. Same way, if we want to divide a by b, then we keep subtracting b from A, and then this difference we again use, and that is used to subtract again by b. So we keep subtracting b and count how many times we subtract b, and at the end when we reach 0, then we just look at the count how many times the b was subtracted, and that count gives the answer a by b. But the question comes is, if b is equal to 0, then a minus 0 is a minus 0 is a minus 0 is a. It will never go down to 0. Therefore, this loop continues forever, which we call an infinite loop. So similar way, today we understood that if anywhere we are trying to divide, first we make sure that the divisor is 0 or not. If it is 0, we stop execution itself. If it is not 0, only then we continue. So this just we stop whenever we get a dividing operation, we just stop and see what is there at the divisor level. If it is 0, we don't divide. If it is not 0, then the division process is continued. But there can be some issues in our user program where it may end up with an infinite loop. Like if we are going to use something like a while loop, and if we say while a goes greater than 0, we just continue. So if we start from a negative number and then keep adding some positive number to that, then from a negative number getting added positive numbers, after a few number of times, it will cross 0, and then we can stop it. So uh, otherwise, if you are saying that you are just trying to continue the loop only when the value is positive, that means while a is greater than 0, repeat it. In that case, we need to make sure that we start with a high positive value and then keep subtracting some positive value from that. And so because of that, it goes down, 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 and sometimes it crosses 0, which stops the process. But by mistake, we are looking for stopping as a negative number. So we just write that while a greater than 0, repeat the following set of code, and we start a with a positive number, and in each iteration we keep adding another positive number to that. Then it will never get into negative side, it will never reduce, and it keeps on increasing and increasing, and all the time it remains in the positive side only. And because it is in the positive side, the loop continues. And by mistake it has happened, we wanted to subtract a positive number, but we added a positive number by mistake, and this gets into an infinite loop. So there is possibility of the human error, then the program may continue to run forever, and it is the operating system's duty to ensure that the program, the user program, should not work forever. So it should somehow prevent these infinite loops. So this is done by periodically interrupting a program's execution and allowing the operating system to regain the control. So just make sure that if it is going round and round, then you ensure that the operating system interrupts the process. So you just imagine that we have some code written here which is getting into an infinite loop, and then when this code is started to run same time, and timer is also initiated, and we know on average, on the worst case, what could be the user mode code takes to run. So if we know that in the worst case how much time any user program can take to run, then we can just create a timer of more than that time and just wait. And within that time, if the loop completes, then no issue. But even after this interval of time, if the loop does not complete, that means this might have gone into an infinite loop. So to stop this, the interrupt has a counter, and it just keeps counting the time, and when the time is up, it interrupts the process and then gets back to the operating system and says this process was running and it ran out of time and hence it was interrupted. Either a user should interfere and see what went wrong, correct it. Otherwise, each time it comes out the same way because if it is any human mistake in coding, then human has to interfere and then correct the mistake. Or if it is happening because of some unavailability of the resources and all, then it may restart automatically and then again can wait for this every time a timer begins and after a scheduled time, if it doesn't complete, then again it interrupts and operating system interferes and gets control and continues. Then one major confusion or wonder is how does a computer starts working? How does a computer starts working? Because as we know that the operating system stays in the back end, that is in the secondary memory, until it comes onto the main memory, the computer cannot start working. And the problem is how to get the operating system onto the main memory. That's the biggest challenge. And that big challenge is taken care by the bootstrap effect that is pulling itself up. That means that we need some process that initiates automatically. So we just have one uh, BIOS, basic input output software system, whatever we can call, which is hard stored in something like a EEPROM, and this EEPROM is part of the motherboard. And when we switch on the computer or when we restart the computer manually, then by default the address is reset to some constant value and the process will start loading from the address which is by default starts, and that default address is pointing to another small code which we call a loader, a small code which is dumped into a small memory, EEPROM, which is non-volatile memory, and it stays with the in the chip, so it doesn't gets deleted even when there is no power supply. So it's a non-volatile memory, and then whenever we switch on, then automatically the processor address gets to the by default address, and that default address is pointing to the BIOS, and this BIOS is a loader, and this starts running. And once this starts running, what is it doing? It looks where the operating system is in the secondary memory, and that from there it start loading the operating system from the secondary memory to the main memory. Byte by byte, byte by byte, it reads from the secondary memory, dumps onto the main memory at a particular location decided in the beginning in the by the system developer, and this whole thing gets dumped onto the main memory. That is done by the bootstrap loader, and what actually happens at this level is a small part of the operating system which we call the kernel gets loaded first. So overall, first what happens is when we switch on the BIOS on the EEPROM gets start functioning, which is a bootstrap loader, and that loads from the secondary memory onto the primary memory the kernel, a small part of the operating system that is sufficient to keep the system active. That means it will allow keyboard active and then the display. So the keyboard and the display are turned on. So that's what the beginning of the session. So when the kernel gets onto the main memory, then the transfer of the control is transferred to the main memory, that is the kernel, and the kernel now starts running. And once kernel starts running, it gathers other information, that is what all the components are connected to our system, maybe the peripherals, maybe uh, other devices like the mouse is connected, or the any other pen drive is connected on all that. So whatever peripherals are connected to our system, it identifies what all are connected, and to work with them, we need a driver software. So it gathers the information what drivers are required to interact with the peripherals, and searches in the secondary memory where these drivers are available, and those drivers are loaded onto the main memory. And this whole thing happens whenever we switch on a computer. So when we switch on the computer, first part, the loader starts working. The loader is called the bootstrap loader, or the basic input output system, which is stored in the EEPROM. It starts running, and this EEPROM is a small code which loads the kernel code of the operating system onto the main memory. After loading the kernel code onto the main memory, the transfer of the processor is shifted to the main memory. Now onwards, the contents of the main memory are being executed. So till now, the contents of the BIOS or the EEPROM code was being executed, and once this kernel is loaded onto the main memory, the control is transferred to the main memory kernel component of the operating system, and hence now onwards the kernel takes the authority and it starts running. And the first activity kernel does is searches all the components connected to our motherboard, and then driver for each of them is loaded onto the main memory, and then the whole full-fledged operating system comes to active mode. So looking at what kernel boot system is, it's a process of starting a computer and loading the operating system into the memory and making computer ready for use. So when we power on the computer, the BIOS performs the post, and then from the disk to the RAM, the operating system is loaded. So that's in general we can speak of. But more detailed version. So whenever PC is turned on, the BIOS is loaded, and this BIOS will run, and from the zero disk, the code is loaded, and that is run, and then this boot sector code looks for and runs the boot manager, and then the details of the operating system are all dumped onto the main memory. So other way, in total, if you look at it, so it first thing is the boot is BIOS is loaded, then power on self test, which is what we call POST, is then completed. So it just looks what all components are there, whether keyboard is connected or not, and display is connected or not. So without display, there is nothing we can do. Without keyboard, nothing we can do. So two things are essential to begin with, and today even mouse also has become essential. So before working, so if keyboard is there, then we can start working. If keyboard is not there, what should I do with that? So when there is no keyboard, and if the display shows, what can I do? I can't tell anything to the system what to do. So minimum keyboard is required, or I need a mouse to begin to see the GUI, or if I want to use CLI, then keyboard is essential. So without that, there is no meaning. It so first it will check, do we have all the basic required things? If yes, then start loading the operating system, and then configure the system accordingly. That means just look at what all components are there connected to our system, and then all the drivers and all are loaded, and then if they are properly configured, and then utilities are loaded, and finally the user is authenticated. Only after that user is allowed to use the system. So that's all the operations, the early operations any operating system will do. So that's some details about the various operations performed by the operating system at a basic level. Many more issues to discuss in the coming sessions of this series. So please keep watching. Please like this video and then subscribe to the channel, and please hit the bell icon so that the coming videos you will get a notification. Hope you are enjoying this session. So keep watching. Thank you. Hi friends, welcome to another episode of this series on operating systems. Now let's look in detail what the system calls are, what are the application programming interfaces. System call is an interface for operating system services. The only way the user programs can safely request services from the operating systems. As discussed earlier, the user programs are working in the user mode and the operating system is working in the kernel mode. And user programs don't have direct access to the services that are working in the kernel mode. To make the things secure, kernel mode operations are hidden from the user mode services. So to ensure that the user mode actions can be connected to the kernel mode services, we do use this called the system calls. So that's a gateway between the user programs and the hardware managed by the operating system. And this figure clearly shows what we are talking all about. So the overall system works in two modes, one in the user mode, one in the kernel mode, and all the user applications do work in the user mode. And if they want to make use of any services that are working in the kernel mode, then they have to go through what we call system call interface. And this system call interface will allow the services to be availed by the user programs, user functions, and so on. Then we have what we call application programming interface. Application programming interface is an interface between the user program and the system call interface. So system call interface is the interface between the user mode and the kernel mode. So user program will uh, send a function calls to the API, and that API will forward it to the system call interface, and then system call interface will send a system call to the kernel, and the kernel works with that function, and that whatever is the result of that function, the values are returned back in the same way. So from the kernel to API through the system call interface, and from API it goes back to the user program. And then in doing this, we do have mechanisms like trap or interrupts that used to switch to the kernel mode. So whenever we are working with the user program or the user application is working in the user mode, and whenever we try to open any file, say we want to open a file, then we just call a system call open, and this open system call will interrupt the process, whatever process is going on in the user program, it is stopped there, and then the whole transfer is transferred to the kernel mode, and the kernel mode, the operation is executed. So we wanted to open a file, say, then we just called a function called open, and then it goes to the kernel mode, and then searches where that open function is defined, and then it goes to the open function, and then it is running the open function and then returns the result, and then the result in turn is returned back to the user application. So that's all operations are performed. So for performing this operation, we do use what we call a trap or interrupt. Trap is the one which is a hardware interrupt. So a pin on the processor is dedicated for this and has got a highest priority. So when it trap is run, that means the pin on the voltage on that pin is changed high to low or low to high depending on the design of the processor. And once the value on the pin changes, then the processor understands that somebody wants to stop the activity, whatever the processor is now doing. So it stops. So whatever it was doing, it just stops. Stops means it just stores all the current environment onto the stack, stores all the current environment onto the stack, and then addresses what is required. So when we use a trap or interrupt, hardware interrupt or software interrupt, whatever, it is used to switch from the user mode to the kernel mode. And once it goes into kernel mode, the kernel functions start working. And before going into the kernel mode, the status of the user program is safely stored. The environment of the user program is safely stored onto the stack. And when we return back from the kernel mode back to the user mode after completing this system call and back, the whole environment is restored from the stack. So the process execution is going on, and then the signal from the user program. So it says we want to execute some function, and that function is defined in the kernel mode. So it just calls a trap, and then the execution enters into the kernel mode, and then whatever trap it was called, so a handling software is defined in the operating system and says whenever this trap is activated, what to do. So is as an example, if we are trying to say that we want to read the keyboard and we are not sure when the key is pressed and all that, and the keys are pressed at the human speed, and the human speed is very slow as compared to the system speed. Human reaction time is in milliseconds, whereas the system is working in nanoseconds. Therefore between fastest two keystrokes, it will be in milliseconds. That means in that milliseconds it could have done millions of other activities. The processors could have done millions of other activities. So in order to ensure that the processor is allowed to continue working, so we just keep working with the whatever processor is doing, and whenever a key is pressed, then the operating system is informed that a key is pressed. So through either trap or an interrupt, the keyboard will send a message to the processor saying that the key is pressed, and then the handler knows that this interrupt is come from the keyboard, and it knows that this interrupt comes only when a key is pressed. So the only operation we have to do is which key is pressed, that information we collect it, and then process that and then continue. If the pressed key has got some valid reason or valid action to be taken, then that action will be taken by the trap handler and then gets back to the user mode and so on. So this is what happens when we make use of the functions defined in the kernel, but user is trying to use them. So when the user is trying to use the functions defined in the kernel mode, then user cannot directly interact with the functions, therefore has to make use of services of the operating system called the system calls. And whenever a user application calls, then the API comes into the picture, and this API will translate the user's requirement that is understood by the system call interface, and this system call interface in turn will translate that into the kernel language. So API is, roughly speaking, we can say that the user program wants something to be done by the kernel, some operation to be performed by the kernel, and user cannot directly run that kernel function. So user will request API, API will request SCI, and SCI in turn will request the kernel saying that this is what user is wanting, and the kernel will execute that function, and then whatever the result of that function is there, the values are returned back to SCI, then back to API, and from that it goes back to the user program, and now the user program knows that what is the result of the system call it had requested. So that's some ideas about what system calls are, what APIs are, and just the whole requirement of these two is because user is not allowed to interact directly with the functions that are running in the kernel mode, and to ensure the security and safety of the system, the operating system is working in two modes, user mode and kernel mode. All the resources that are to be used, all the functions that are using the resources will be working in the kernel mode. So very serious and strict supervision is being monitored while working with kernel mode operations, and hence it going to be very much secure and all that. And the user application need not be always foolproof. Therefore, before using any resource, we have to doubly ensure that nothing wrong can happen. So for that, the user is allowed to request the kernel through API, then to SCI, then back down to kernel. And only if the user request passes through all these three, then only the kernel will be executing it. So it's a lot of hindrances, a lot of security gates are there on the way. So that makes the things more secure. So that's it for now. Many more issues to follow. So please keep watching. Please like this video and subscribe. Refer to your friends to refer and watch these videos. Subscribe, and please don't forget to hit the bell icon so that the next video is coming, you get the. Now let's get into some details about the operating system functions. As we discussed in the beginning of the series, that the operating system performs several functions like process management, memory management, disk management, networking, security, device drivers, and user interactions and all that. So let's see what all it can perform. So under the process management, process basically is a program in a running condition. So as long as the code is there in the backend, that is secondary memory, it is called a program because it doesn't have any state, doesn't have any action, it's just a code. But when we start executing it, then this code comes onto the main memory, and once it comes onto the main memory, it is named as a process because this process contains, along with the code, the memory to store the variables and the memory for the stack and all that. So the whole thing which contains code, then the memory for the variables, the contents of the variables, and the stack all together will be called a process. So under process management, creating a process, that means getting the program from the secondary memory onto the main memory. That means before getting into that, we need to allocate the memory and then decide where what goes and all that, and allocate the memory for various variables defined, and allocate the memory for the stack and all that. This whole thing is done under what we call creating a process. And once the work is done, then we need to free the memory. We need to give the space for others to occupy. So the deletion of the process also under the process management system. When we are trying to run multiple processes on a single process environment, or multiple processes on a single processor environment, then any given time only one process can be active and all other processes have to be inactive. Then when multiple processes require the service of the processor, then it cannot be given in any way we want. It has to be done in a proper way, and that proper way of providing the fair chance for every process to get the opportunity to use the processor and get its work done. That's what we call scheduling. So we see various types of scheduling algorithms available under the process management. Then we need to synchronize the various processes. If one process wants to communicate with another process, then there has to be some great synchronization. Say two processes are trying to communicate and one process wants to send a message to another process, then the other process should keep waiting till the first process sends a message and the second process receives it. So there has to be some synchronization between the two processes and multiple processes if we are working in such an environment. Then all the synchronizing activities and communication activities and all are taken care by the process management. So the next important action is about main memory. Yes, we do have limited memory available as a main memory, and this limited memory we should use to full extent as much as possible. So there is a requirement of allocating the memory for each process. So how to allocate the memory? Under process management also memory allocation is done, but it just tells that how much memory is required for the code, how much memory is required for the variables, how much memory for the stack and all that. It doesn't care where the memory is available and all that, but the memory management is the one which verifies the availability of the memory and then allocates the various components, the memory for the various components. And this is taken care by the memory management component of the operating system. And once a process completes its actions, then the process no longer exists. And when process no longer exists, then the memory occupied that process is a waste of memory. So instead of that, it should be released and given for other process because memory is limited and it is very precious. So we must ensure that the moment a process completes its task, the memory has to be deallocated. So this allocating of the memory, deallocating of the memory, and all this are taken care by the memory management part of the operating system. Then it keeps track of memory usage, how much memory is being used, where the memory is being used, and all that, so that it keeps track of free memory. And when a new requirement comes up, then it should be ready to allocate the free memory for the new requirements. And then it also must ensure that the two processes are kept in isolation. That means there should not be any overlap of the memory usage by more than one process. So every process should be allocated a unique memory, should not even by mistake one part of the memory should not be allocated to more than one process unless until it is required, what we call a shared memory. But as long as no such shared memory requirement is there, then each process should be allocated a separate memory so that there should not be any misunderstanding, there should not be any miscommunication, there should not be any overriding of the data and corruption of the data and all that. So we must ensure that each process gets a different part of the memory. No overlap and all that. So that is also taken care by the memory management component of the operating system. Then comes the files, the file system, what logically we refer as a file is just a logical entity. It doesn't. We don't have to worry about where exactly the our information is stored in the secondary memory and all that, and how it is stored. We are not bothered about that. We are only bothered about file structure, like directories and how many directories are there in each directory, what all we have, and are talking about any particular file. Then what is the path of that file from the root directory, how to reach that file and all that. That's a part of the file. So these are the things which matter to us. So when we are creating a file, we do require some actions to do. So in the backend, some memory has to be allocated, and that has to be put in the part of the directory system. The name of the file should be given, and type of the file should be given, and all that, and the access control, who should have what type of access control, whether anybody can only read or can read, write, or modify. Any such access controls are also to be decided under this file system management part of the operating system. So creating a file, deleting a file, reading a file, writing a file, and directory operations, all these come under the file system management. Then it also talks about the permissions for each file directory, whether the one owner of the file, what rights the owner of the file has got, what rights others have got. So usually we say that owner of the file can access the file in all possible ways, but others, we want others to only read only like thing, or they may read and write but cannot execute and all that. So there are three types of permissions: one for read, one for write, and one for execution. At the same time, there are different types of users, like normal user, outsider, and then the part of the group, and the owner of the file or the directory. So each one may be given a different access control permissions, and security uh, component of that is also taken care by the file system management part of the operating system. Then mounting the file systems, so how the file system is connected to the directory, which directory this file system is connected, all that. So we have a proper tree structure of the file system, so that it becomes easier for creating and accessing any file, and a unique way of accession is possible for every file and all that. So these all are taken care by the file system management component of the operating system. Later comes the device management, where we keep talking about various IO devices connected to our system. So when you are connecting IO devices to the system, usually the IO devices will be very, very slow compared to the processor or the system itself. Then if we are interacting with any slower IO devices, then it is better to have some buffer memory in between the system and the IO device, so that if we are reading any data from the input device, then instead of making the processor keep waiting for each bit of the data to come in bit by bit or byte by byte, and takes a hell lot of time, so we can allow the IO devices to work with the buffer. So the input device is reading something, and then let the data read from the input device is first put on the buffer, and now and then the processor can take time and read the data from the buffer, instead of waiting for the IO devices, which are heavily slower compared to the processor speed. Same way, caching and spooling are taken care by the device management. Managing the device driver, so each device behaves in a different way. So to ensure that the behavior of each device is properly understood by the system, we do have something called drivers, and these drivers to be managed, and this is done by the device management system. Then comes the secondary drive, that's the storage management. The storage is divided into partitions, and then disk partitioning, formatting, and all that is taken care by the storage management, then space allocation, and then tracking. So if we want to write a file onto the secondary memory, and this file needs some space in the secondary memory, so which part of the secondary memory we can allocate the space. So it may be at a stretch, or it may be allocated at different partitions, different slots, and all that, depending on the way the storage management is done. So many issues about the storage management we need to look at. So main action done by that is about how the disk is partitioned, and how the what is the format used for the disk. So if we know the format of the disk, then the communication between the secondary memory and the main system becomes possible. Then space allocation, and then tracking where the space is available and all that. And then scheduling, because if one file is stored onto the secondary memory, and if that file is stored in smaller chunks here and there all over the disk, then you can just can't keep moving randomly as and when it is required. So if we have a proper movement of the disk possible, because basically disk is a mechanical system which works on a rotation, and the tracking is done by the heads, and all that movement of the heads, rotation of the disk, and all that have to be taken care. So to make sure that the part of the file which are distributed all over the disk are read, and instead of reading in any random way, if we can read it in a proper way, then with minimum number of movements of the disk, minimum number of movements of the reading element, we can ensure that all the data can be read or written. Because movement means physical thing, physical means it's lethargic, and it is highly slow, and definitely the speed of this movement, head movement, and all are totally incomparable with the speed of the processor. So make sure that all these activities are done as early as possible, so that the whole system works more efficiently. That is taken care by the descheduling component of the storage management of operating system. Yes, security and protection are major issues to be taken care by the operating system. So whenever a user tries to interact with the system, then the authentication, some logging system has to be implemented, and make sure that this authentication system is highly secure, so that the whole system can be well protected. Then proper permissions and access controls for every part of the system should be very well monitored, and well defined, so that nothing goes wrong. Then isolation of the processes, as we discussed, so that also should be taken care. And finally, the networking part of that, the communication management. So we need some protocols, some standards to be set how two systems should communicate. Like example is, if we trying to communicate with another human, a human is trying to communicate with another human. So first thing required is a common language. Unless until we have a common language, two humans cannot communicate each other. Even that common language may be a sign language, or maybe any spoken language, but it has to be one common language, and that common language has to be decided prior to communication begins, and that is what we call a protocol. Protocols have to be defined, and this support of these protocols have to be taken. So when you are working with multiple systems, and if they are interconnected, then we should ensure that each of the system is working under the same protocol. Only then communication is possible. If multiple people are trying to communicate with each other, then one thing is essential, that all of them should communicate with a language which each one of them can understand. So that's what we infer as a protocol. Then how to manage the network connection. So when we are trying to connect one system with another system, how the connection is done. So it can be a synchronous connection or it can be asynchronous connection. Many situations are there, many different versions are there, many types are there. So there are some elements like sockets and all that that are useful for connecting between two systems. Yeah, it's a socket, not necessarily means the physical socket and all that. It's an logical name. The socket is a software tool that helps us in connecting two systems, which make sure that connections are run between two systems for using a proper protocol, having proper security system and protection system enabled, and all these. So this whole activities are under the control of networking management or the networking component of the operating system. So that's a overview of various functions that our operating system can give to us. So let's get into these one by one and see in little detail at this instant. We are not going in full detail. We are still in the introductory part of the session. So let's just get a bit better glimpse of what each of these are in coming sessions. Once we are through this, then we get into deep and see each of these components and how each one of them are implemented and what are the issues with each of these components and all that will be following in the future sessions.
The
So that's it
overview of
for
the
now.
various
Thank you.
functions provided by the operating system. First, let's begin with what we call process management. The process management has various functions like creating a process and terminating a process, scheduling the process when we have more than one process which is being active, but there is only one processor. When any given time only one process will be working, all others have to remain inactive, and this is taken care by the scheduling of the process under the process management. So when the process is interacting with the IO devices and other peripherals, then there has to be proper synchronization. So that's taken care by the process management. The communication among the processes is another activity taken care by the process management. There are various resources available, and these resources have to be properly shared among the processes, and this responsibility is also with the process management system. Then each process will be in different states depending on what currently it is doing. It may be a state where it is waiting for the CPU for its turn, and that's a waiting state. And once the CPU is made available for this process, then we say it is a running state. And while running, if it wants to interact with any slower devices like IO devices and all that, it can't wait there, so it just come out of that and starts again waiting for the response from the IO device. But there are two types of waiting. One is waiting for its turn to get the CPU, that is the scheduling, and another one is waiting for the response from the IO device, which is very, very slow. So all these things are taken care in the process states, and every process is given with the details, and these details are stored under the process control block. So what's process management? It's essentially used for efficient resource utilization. It maintains the stability of the system, making sure that the resources are properly allocated to the various processes so that everything runs smoothly, so there is no instability in the system. Very much useful when we are working on multitasking and multi-programming environment, and makes the user experience more smooth, and gives a simple work for the user to do. Most of the work is carried out by the process management component of the operating system. So looking at the process management, so first we just like to define what a process is. A process in turn is a program in execution. So as long as the code is there in the secondary memory, then it is called a program. But once we start running it, or when we wanted to execute that, the first step happens is this program is loaded onto the main memory. So when it is loaded onto the main memory, then it becomes a process. And along with the code, it will also have its own state, whether it is in waiting state or it is in the running state and all that. And along with that, the data of various variables and all that also is stored along with that on the main memory. All these three together will form a process. And this details about a process are stored in the process control block, where the various components are there at any given time. What is the process state? What is the process number? And what are the components of the registers, memory limit, and what are the files that are opened by this particular process, and exactly where this process uh, is situated. So pointer to the process and all that are available in this. More details we get into when we see the process management part in detail in the coming sessions. So just an overview we are giving here. So various states are there. So when a new process is formed, that means when we won't like to run any new program, then the first thing happens is that program comes onto the main memory from the secondary memory. So whenever a main memory is written by the code, then that code is now onwards called a process, and that's a new process. And once the new process is made available, then it gets into the ready state, that it is ready to be run. And whenever the CPU is free, this particular process is allocated to the CPU, and CPU starts running it. And while running it, it may end up with three situations. One is many processes are waiting for their turn. So we may allocate a fixed time for each process. Then once that time is over, then it is interrupted, the processor is interrupted, and because of the interruption, the current process gets into the ready state back, and another process which is ready will start running. Another option is that it wants to get some input from the external device, like IO devices, maybe keyboard or the secondary drive and all that, which are very, very slow compared to the processor speed. Therefore, it's not advised to wait indefinitely for the slow inputs available. So we can just stop the process and keep the process under waiting state, and let it keep waiting for that particular event to happen, maybe that reading event or writing event. Or once the event is completed, then the process gets back onto the ready state. The third possibility of getting out of the running state is it has completed its execution, then it exits, and then it gets terminated. So this is the overall situation we have. So when we are working with multiple processes, what exactly we are trying to do is multiple process, maybe one word processor is open, one email system is open, one web browser is working, one antivirus is working, and many such things. We are keeping them open simultaneously, and all of them may be working and on a logical level if you look at it. So on one side, one of the browsers may be downloading some file from the internet. On the other side, we are typing something on the email. On the other side, we are trying to upload some document on the email and sending to someone else, and the backend, the antivirus is working and all that. But whatever it is, but when it is being executed, it has to be done by the CPU or the processor. And in our earlier system where there was only a single processor, then under a normal case, only one of them should be working. But to make sure that everything is running simultaneously, or to logically show that everything is working simultaneously, just because we know that the human response time is quite slow, very, very, very slow compared to the processor speed. Therefore, on one side you can make the email, we can keep typing on the email. On the other side, one more email maybe downloading something, and the third side, one more email maybe we are uploading some document onto the email and all that. All these operations for us, a user, it appears to be done concurrently, but in reality, they are not done concurrently, because to do these actions, the processor is required, and we do have only one processor, and this one processor has to be used for all this. So some sort of scheduling is done by the operating system. So it allocates one process at a time to the CPU, and then CPU works for that. And if these are done at a high speed, then we logically think that all of them are running parallelly, but in reality, only one will be running at any given time. So that's what a major contribution of process management is what we call scheduling. So we can just look at the same situation in another way. So we have a ready queue. So all the processors which are ready to be executed will be available in the ready queue, and the one which has come earlier on the queue is allotted the CPU, and if it has completed its job, it just moves out, or it may stop execution for reasons like the process has asked for some IO request, and IO is very very slow because there is human interaction required, like keyboard reading or mouse reading, or maybe even we are getting the data from the secondary drive like hard disk and all that, which have mechanical movements and all, which are very very slow compared to the speed with which the processor is working, the motherboard is working, and all that. So instead of keeping our CPU waiting for all this thing to happen, we can just say that let me stop working with you. You take care about your IO, and then once you are ready, tell me. So it just stops the execution whenever it gets an IO request, and when we get an IO request, it puts the IO request onto the IO queue, and then whenever that IO system is available, it is executed, and then once it is done, it comes back to the ready queue. The other thing may be for each process a time slot is allocated. So if that time slot has completed, then on the expiry of this time slot, the CPU stops executing that particular process and takes up another one. So once the allotted time is over, then it's put back onto the ready queue, and it keeps waiting for its turn. Otherwise, the process may create another child process, and will wait till the child executes its work, and once child executes its work, it will come back to the thing, or it may be interrupted for some other issues. So wait for the interrupt. So we have asked for IO device to get something, and IO device is getting it. So once we allot the work to the IO device, it starts working, and then when it puts the data onto some buffer, and once the data is put on the buffer, then the IO device will interrupt our processor, and this interrupt completes this task, and then get back to the ready queue. So this whole thing is something to do with the scheduling. Scheduling, we have two types of scheduling. Scheduling means assigning the CPU to the processes. So we have two types of scheduling. One is called preemptive, another is called non-preemptive. Preemptive means the processor has a right to stop any process in between and get serving some other process. So that's a preemptive scheduling. Non-preemptive scheduling means once a particular task is started executing, till the execution is completed, other tasks cannot be taken up. That is non-preemptive. Under preemptive, we have different types like priority scheduling, shortest remaining, or longest remaining, or round robin. On the non-preemptive, we have first come first serve, shortest job first, longest job first, or highest response ratio next, like different types of scheduling algorithms. So let's look at what the preemptive scheduling is. In the preemptive scheduling, the operating system can interrupt a running process and switch to another one. Yes, that's what we meant by preemptive scheduling. That is, now operating system can say, stop, your term is over. Now let's give chance to some other process. Here, it's not necessary that the process should have completed its work. So even if it is not completed, it can stop. The stopping may be for various reasons, like the allotted time is over, so something like a round robin, like scheduling, or maybe some more important task has come up. So if this less important task have to stop and wait till the more important task is to be done. So that's a priority scheduling and all that. Then we have another type of scheduling which is called non-preemptive. It's the running process cannot be interrupted by the operating system. So once the process starts running, the operating system has to wait till that process completes its job. Both have their own advantages and disadvantages. We'll see what each one is going to talk about. So the basic the preemptive scheduling allocated a process for a limited time, whereas non-preemptive scheduling there is nothing like allocated time. So it is made available. The process continues to run till the process completes, or maybe because of external IO requirement and all, it may get into waiting state, but it will not go into ready state again. So once it will be in the ready state, ready queue, then once it is switched to the running state, then it will not go back to the ready state. It can go back to ready state only through the waiting state. So as far as the interrupt is concerned, the process can be interrupted in between in the preemptive scheduling, but in non-preemptive scheduling, nothing can stop it. overhead. It has got overhead of scheduling process, and in this non-preemptive, there is no scheduling overhead. Whereas preemptive scheduling is flexible and the non-preemptive is rigid. So if you are given the sequence in which a process has to run, then it will always follow that particular sequence until the work is done. It will not stop. So some of the advantages, disadvantages of each one, we can see that now getting into the preemptive scheduling. One example will be the round robin. So many processes are there, only single process is there. So in the first, we can give a process one maybe 3 units of time. After 3 units of time, it gets into a process one maybe of 3 units time, but each one is given 2 units of time. So after 2 units, process two gets in. Then after 2 units, process three, then process four, then process five, then process six, then process seven, and then process eight. In the process one, it wanted 3 units, but we have provided only 2 units in the previous cycle. So now one more unit is required. So 1 unit of time is again given to process one. Then 2 units of time remaining is given to process two. Process three wanted 2 units, so it was given 2 units. So no more process three is existing. 1 unit of process four is still pending. So this way it keeps on doing. Then we can think of shortest remaining time first. So among the various processes, just look at what are the timing the each process wants. So some halfway it has run and any some more time it has to run. Then look at which process needs shortest time. So allocate that. Or we can go for priority based. So whichever process, when more than one process wants to be executed, then look at the priority of each of the process. And the process which has got highest priority will be given first chance, then the second priority, then the third priority, and so. So the reason for calling this priority based, because when some low priority process is running and at that time high priority process comes up, then the low priority system is forced to stop, and then chance is given to the high priority system. If no high priority system is available, then the low priority system will be allowed to work, low priority process will be allowed to execute. But while low priority process is running, and that time if high priority process comes up, then the low priority process is stopped. So preemptiveness is required for that. Under non-preemptive, it's just a first in first out queue is used for that, and whichever has requested first will be given the chance first. So just a queue is sufficient for that. Don't have to worry about timing and all that. Whoever asks service first will be given chance first. And shortage of first is another one. So when we are given with multiple processes, then just look at that which job requires shortest time, then first allocate uh, CPU to that one and all that. So with this, what happens is the average waiting time will reduce. For more details, we look at when we are actually working with in our next module, when we look at process management in detail. Then we have priority scheduling. So depending on the priority, so P1 has got priority 2, then P3 has got priority 1, and P2 has got priority 0. Therefore, the order in which it was run was highest priority 2. So P1 runs first, then next priority 1, that is with P3, then next priority 0, that is with P2. So P1, P3, P2, this way the processes are run.
Now, after looking at the process management component of the operating system, now it is time to look at what memory management is all about, how the memory in a system is used and configured and all that. So when we say memory, we mainly talk about the main memory or the primary memory, which is there on the motherboard. Usually it's a random access memory. So we have two types of environments when we are working with memory. One is a uniprogramming environment where any given time only one program will be under process. So the example would be the old version, that is the disk operating system type of operating system, where anytime only one program will be on the main memory. So we don't have much problem with such things, because anytime one program will be on the memory, therefore the requirement of the memory is small, so it doesn't make much problem. But later, with the improvement in the technology, with the development in the technology, the memory become cheaper and all that, and we are now able to offered more amount of memory on the board, and then we realized that a lot of memory is available. Then instead of loading one memory, one program at any given time, we can program work with multiple programs at any given time. So we get into something called a multi-programming environment. So when we are working on the multi-programming environment, then on the same memory, more than one program will be loaded onto the memory. So on any given time, more than one process will be there on the main memory, and for each process, we will require memory to store the code, memory to store the data, variables, uh, and stack, and so on. So this memory, we started working with a contiguous allotment. So whenever a process comes up, it requires a memory, and when it requires a memory, then a contiguous memory is allocated to that. And this contiguous memory allocation would be either a single contiguous allocation or a partitioned allocation. And when we had a difficulty in allotting contiguous memory, then we thought of working with non-contiguous memory allocation, under which we have a paged memory management and the segmented memory management. So we can divide the memory into segments, and each segment may be allocated to the process, or the whole memory can be divided into number of pages, and depending on the requirement, each process will be given some number of pages, and that's how the whole system works. So the major goal of memory management is to allocate and deallocate the memory for any given process. Then the address translation, like logical address to the physical address, because at the process level we are only bothered about the logical address. We don't bother in exactly where the data is stored, where the particular code location is, and all that. So we are not just bothered about all these things. We only bother about the logical addresses. So we don't bother about physical addresses. It is the memory management component which takes care of these translations from the logical address to the physical address back to the logical address, and all that. So all these are the work done by the memory management system. So we have two major techniques. So it can be a contiguous memory allocation. Under contiguous, again, it may be a fixed size or the dynamic size. And there is non-contiguous, like just discussed, it's a paging. Now looking at the contiguous memory allocation, then again we do have two types of contiguous memory allocation. It may be a static partitioning, where each process or each component of a process will get a fixed amount of memory and has to work with that. So this usually works when we are talking about defining the variables. Like if you define, say for example, in C language, if you define a variable of type integer, then 2 bytes of memory will be allocated to that. If you define a variable of floating type, then 4 bytes of memory is allocated. So these all are fixed type of memories, and depending on the number of variables, the fixed size of memory will be allocated to each of these variables. On the other side, we have a dynamic partitioning. The dynamic partitioning, we do make use of runtime allocation and deallocation. So in the static partitioning, it is a compile time allocation, deallocation. So like you want to define an array, then the array will be defined in the code itself, that the array is with a particular name, is of particular type, and has got so many number of entries, maximum size of the array. Say if I define A as an array with 100 elements in that, and it's of type integer, then memory will be allocated to array A with 100 elements, and each element will occupy 2 bytes if it is working in C language, then 2 bytes for each element and totally 100 elements. So in all, 200 bytes of memory will be allocated to the variable array A. But when you are defining array, we define in the code itself and say that we want array of size 100, and we are not sure that how many of these are going to be used. So when we are working on that, then we just try to find out what could be the maximum number of elements we can use under that array. So using that logic, we try to define in the code itself. That is, during the compile time itself, memory has to be requested, so how much memory is required and all that, and that's what is the fixed size of static partitioning is. But when we are working on the other side, some of the data we don't know how much is required, and like we did in the array, we try to use the worst case, and in the worst case, what happens is most of the time the memory is underutilized, and not to underutilize the memory because this memory is very precious and very costly. So we just want to use the memory to full efficiency. So to make sure that the memory is never wasted, we switch ourselves to the variable size partitioning or the dynamic partitioning, wherein the memory is allocated or deallocated during the runtime. So that's a difference between the static partitioning and dynamic partitioning. In both cases, we are trying to talk about contiguous memory allocation techniques. So just look at the pros and cons of each of them. The time of allocation, the static allocation is done at the compilation time. That is when we are writing the code, we define that this is a variable is of type array, and then elements of in that array is going to be so and all that. So everything we have to define in the code itself. So while typing the code, we have to write it, and once the code is typed and compiled and the executable file is created, then it is not possible to modify this. Therefore, we call it the compile time allocation. Whereas in dynamic allocation, it is done at the runtime because we never type anything in the code itself, but we try to make use of some functions we look at the next time. So the memory size under static allocation is fixed, so we can't modify that. But when the dynamic allocation it is flexible, we can increase or decrease the size of the memory as per requirement. So we can more efficiently make use of the memory usage. For example, in the static allocation, we have define the global variables and static variables in the code itself, then that is what the static allocation is. But in example of C, there are functions like malloc, alloc, and realloc and free. So these are the instructions used to allocate the memory and deallocate the memory and during the runtime, and that can make the size of the memory use and can be made flexible. And looking at the efficiency, the static version is definitely very faster because we have defined the fixed sizes and all that. But the efficiency in case of dynamic allocation is in terms of space, and static allocation is better in terms of time, and dynamic allocation is in terms of space. Yeah, time and space are opposite poles. So if you try to improve the speed, then size becomes a problem. And if you try to make use of efficient use of the space, then time becomes a problem. And of course, memory wastage, it can occur during the static allocation because we don't have exact idea that how much of the memory we can use at any given time. Therefore, in the worst case, we try to fix it. But in the dynamic allocation, it can be uh, adjustable as and when required. Therefore, the memory wastage is least. Then getting into the non-contiguous memory allocation, because the problem with contiguous memory allocation is when we define a new process, then the new process wants a amount of memory to be allocated for that process, and the total requirement of the memory for that process, if it is not available at any given position, then the previous version, that is contiguous memory allocation, fails to allocate it. But though the memory is available in chunks here and there, but it cannot allocate because it wants at one place the total requirement to be fulfilled. But that may not be possible all the time, and hence we fail to allocate memory even if the memory availability is there. So we can just switch our attention from contiguous allocation to non-contiguous memory allocation, where the process may be allocated at different places, like process 1 goes into block 1, process 2 goes to block 3, process 3 goes to block 5, and so on. Then we have something called virtual memory. That's one uh, thing which we would like to work with when our requirement is much more than what is physically available. So the logic here is the physical memory available. If it is less than what really we require, then what we can do is we can convert our requirement into smaller parts, divide that into smaller parts like pages, and then each page may be allocated wherever the memory is available. So in this case, our process requires five uh, pages like A, B, C, D, and E, and then we realize that physically there are only three pages available. So what we can do is we can get A, B, and C onto the main memory, and D and E we just keep it on the back end on the secondary memory. And when we are working with, if A is required, so it is available on the memory. If B is required, it is available on the memory. If C is required, it is available on the memory. So we can just use the data from these different locations. But anytime if the data from the part D is required, then we don't have D on the main memory. So what we can do is we replace one of these three pages, A, B, or C, by D, and then start using that D. So this way what happens is, even if we have three pages available with us, we can make use of these three pages, and as and when required we can keep on shifting the pages from main memory to back end to front end as and when required. And that way it gives an illusion that only with the three pages available we are working with hundreds of page worth process. So maybe during this shifting of pages from back end to front end to back end, which we call page replacement and all that, there is wastage of time, but still we are able to solve bigger problems with a smaller availability. So that is the concept of virtual memory. So here we work with a process called paging, where the pages are logical. So we have four pages: page 0, page 1, page 2, page 3, and these four pages are to be put onto the real physical memory, and those physical memories we do have at different four locations. So these four locations get a chance to use. So page 0 is put at frame 1, page 1 is there at frame 4, and page 2 is at frame 3, and page 3 is at frame 7. So we have the page table which says that you want page 0, go to frame 1. If you want page 1, go to frame 4. If you want page 2, then go to frame 3, and if you want page 3, go to frame 4. So frames are the frames will represent the physical memory, whereas the logical memory is represented by the page. So there is mapping between the pages and the frames, and this mapping is done by the page table. And through this, we are able to. So what is it trying to say now is there are four pages or four frames are made available for our requirement, and we had a requirement of 4 pages, so that is fine. But it may be that there are only 4 frames available, but we have a lot number of pages. In that case, we make use of this reverse mapping of this, so we have uh, frame numbers and then the page numbers and so on. So whenever we wanted to get a data and that data belongs to a particular page and that page is not there on the physical memory or not there in any of the frames, then we say that the required data is not available. So it raises alarm which we call page fault. So when we are trying to load, access some data and that data is supposed to be in a particular page and that page is not there on the physical memory, then we raise a page fault alarm, and when a page fault alarm is raised, then that page which we wanted should be taken onto the physical memory. So to take that onto the physical memory, we need to replace one of the pages which is already there on the physical memory. So for that we do require some replacement algorithms. So it may be the first in, first out. So the whichever page was taken to the physical memory first moves out first. Or it, to be a better one is one page which is not very much in use. Remove that. It means that its purpose might be served. So we can think of replacing the least
The
recently
operating
used
systems,
pages. All that.
one concept at a time. Now it is time to see the storage management, that is the place where the programs, data, and all are stored when not in use. That's a secondary memory. So mainly we are dealing here with how the secondary memory is managed, or as long as far as primary memory is concerned, we have seen in the previous session, that's main memory management. Now let's jump into how the secondary memory and others are managed. So the storage management system consists of the processes and the techniques used to efficiently manage how the data is stored and accessed on a computer's storage devices. There are many different devices. So there are many different types of memory associated with any computer system. So let's first get into what they are. The innermost one that's nearest to the CPU is registers. These registers are directly connected to the CPU and they are part of the central processing unit, the chip, and they are designed. The connectivity are designed with high precision, so they will be working at processor speed. Then next thing comes is the cache memory. The registers are very limited in number, so to make sure that process is speeded up, we need some more memory, and that memory, and due to the reduction in size of the processors due to advancement in the VLSI technology, more and more space was available, and this space was utilized by adding memory into the chip itself, and that was called cache memory. And this cache memory is inside the processor chip, and hence will be working at a higher speed, at almost processor speed. So the whatever space was available, that much of memory was created inside the chip. And if that is not sufficient, then we get out of the chip and we go on to the motherboard. And on the motherboard, we have memory called the random access memory. And this has no space problem, and hence we have a more space available for the data to be stored. So we have a higher amount of memory available here, that's on the motherboard, which we call the main memory, and that's what we had seen in the previous session about the main memory management. Since this is put on the motherboard, it's not very well designed,
So it will be working almost 1,000 times slower than the main processor. And the next one is the electronic disk, usually called pen drives and all that, which are plug and play type of memory we have. And these also are an electronic memory, so there won't be any moving parts and all that, so they will also be working at a higher rate. But only thing is they have to interact with the IO ports, and IO ports usually work in the serial mode of communication, and hence to transmit one byte of data, it should be transmitted in 8 time slots, because each time slot one bit of data is being transferred. So it will be a little slower compared to the main memory. Then we have a requirement of more memory. Then we get into what we call a magnetic disk. That's a hard drive, and this hard drive has got a larger capacity, but the magnetic disk is being used through movement, rotations, and all that, and it's having mechanical movements, and hence is quite slower compared to the electronic memory. And the next one is the optical disk, which makes use of optical, the laser rays and all that, and that will again needs mechanical movement, and hence it is also slower, but can have more amount of data in a given space, because it is working at the light dimensions. And finally, we have a bulk memory, which is stored in terms of magnetic tapes. So magnetic tape is the slowest memory, registers are the fastest memory. So there are so many various types of memory. So here we are not bothered about registers, cache, and main memory. We are only bothered from the electronic disk, magnetic disk, optical disk, or magnetic tapes like things. Most commonly, we are talking about the magnetic disk type of memory in this case, and then look at how individual entity of the data is stored onto that, and it's all that taken care. So when working under storage management, we need to look at how the memory is managed, how the disk is managed, how the files are managed, and how the free space is managed. So these are the various components of the storage management. In the previous session, we have seen about the memory management. Now this is time to look at what the disk management and file management are. So file management is the one which handles the organization, storage, access, and control of files. So how the files are organized on the disk, and how it is stored, how it is accessed, and how the files are controlled so that it is protected from misuse and all that. So the file management also provides a logical view of files, hiding the physical storage details. So we are not interested in where each component of the file is stored and all that, as we were discussing in earlier stage, that the space may not be available at one place, so it can be put in various different places. So we are not bothered about where the data is placed in the memory and how it is placed and all that. We are only bothered about if I want a amount of data to be written or retrieved and all that. I just want to use a name for that instead of going through all the details. So it gives an abstraction, it hides all the working details of how the data is stored inside the memory and all that. It makes no sense to us to know all these informations. What is important to us is name of the file and want to read or write or modify or whatever you are talking. So that, so just we work on a logical level, and at the physical level, what actually happens is taken care by the file management component of the operating system. It manages the file attributes like names of the file, types of the file, size of the file, and the permissions. All these things are taken care by the file management. And coming to the disk management, that means we are talking about how physically things are stored onto the secondary memory. So it organizes and maintains the data on storage devices like hard drives and SSDs. It includes partitioning, formatting, managing the file system, and all that. So it's not just a one a particular entity. It is divided into partitions to make the things simpler, because we have to make sure that the mechanical movements are done as minimum as possible, so that the overall process is speeded up, and what is the format of the with which the data is stored and all that, everything has to be taken care. This is done in the disk management system, and also ensures that data integrity and efficient storage space utilization. So these all are the various components of the disk management system of operating system. So let's just have a little um, extra information about the file system. So file basically is a logical storage unit which consists of data and the attributes. So here we can see that a user is having its own application that gets into the logical file system. Logical file system works with a virtual file system. Virtual file system works with the physical file system, and finally the data is put onto the storage. So as a user, we don't have to worry about all internal details. We just have to talk about what is the name of the file and what we want to do with that file, want to open it or write it or modify it or delete it, create it. All these operations we are only bothered about. And internally, what all things are happening is none of our business. We don't want to waste our time on all that. And these all activities, we just give it to our file system. And then these files for our quick reference and all are maintained hierarchically in the tree format under the directory structure, so that we can easily understand where our file is. Instead of having all things dumped at one place, we can just logically divide them into directories, and in each directory we can have different files and all that, directory, subdirectory, and so on. So it's a logically tree structure is created, so that will help us in arranging the files in a more better way, more understandable, easily placed and easily retrievable, and all that is possible. Then the various operations possible, the file operations, we can create a file, we can open a file, we can read a file, we can write onto the file, we can delete a file, we can close a file, truncate the file, flush, wire, write lines, change across permission, and all that. So these are various operations that are possible with a file. So we want to create a file, so we use the create function. So when you want to interact with the contents of the file, the first thing we have to do is open the file, and when the file is opened, only then we can work on that. So to make sure that the file is opened, the one who is opening should have all the permissions and all that. So this all things are taken care. So these are the various examples of the file systems. It may be NTFC or FAT32 and all that. So some details we are going to look in the coming sessions when we deal with this file system in detail. Now coming to the other part, where the data is physically how they are managed onto the secondary device, which we call disk management. The figure here shows how a disk can be arranged. So it's made up of many disks which are rotated through a spindle, and each disk will have tracks, and each track consists of sectors. So we have a cylinder, then we have a sector. So for that particular cylinder, we have one track on each of the what you say platter or the disk. Then we have an arm assembly to which read-write heads are connected, and these read-write heads move in and out, so that different track can be used. And two use a particular sector, this whole thing is rotated. So when this is rotated, a different sector comes near the read write head, and maybe a magnetic or optical way the reading writing can be done. And that's the whole concept of the disk arrangement. So it is made up of tracks, sectors, cylinders, and so on. So to make sure that a particular data is to be read, then we must ensure which of the disk we are trying to look at, where our data is, on which disk, on which track, and which sector. So disk, we need to activate appropriate read write head, and then track, then this arm assembly should move in and out so that appropriate track can be used, and then for a correct sector the whole system is rotated so that that particular sector comes near the read write head, and the read or write activity continues. Now there are scheduling, because we just want to make sure that the data is put on disk, and we are not sure that the whole file can be written at one segment, or one sector, or one track. So it may be placed at various locations depending on the free space available. So it's not necessary that every part of the file may be on the same disk, or on the same track, or on the same sector. So it may be possible. So to make sure that everything is read properly, then this movement of the heads and movement of the disk should be done in such a way that with minimum movements we would be able to complete all the tasks. So that is what we call the scheduling algorithm, and we have various scheduling algorithms for disk management to make sure that the various components of the file are read from the disk at the earliest with minimum movements, because movement means it needs time, there is inertia, and movement, mechanical movement is very slow compared to the electronic speed. The processor speed is in nanoseconds, and movements and all, if we consider, then they will be working in millisecond speed. That means 1 is to million slowdown is there. So if you want to ensure that the whole process is fast, then we need to make sure that these mechanical movements are made as minimum as possible, and that is taken care by these scheduling algorithms. And then we need to look at what we have, what we call is random disk for performance and reliability. We look at how to improve the performance of the read write activity of the disk. So these are various issues we need to look at when we are working with the backend or the secondary storage. So more details to come. So please keep watching. Thank you. Now let us look at how operating system protects the overall health of the system, and then it secures our applications and all that. So the goal of this protection is to control the resource access, and to ensure that every user is not allowed to work with any resource. The resources are given privileges, and only the appropriate users or applications, or the application interfaces, or the subsystem calls will be allowed to work with a highly privileged system. So in this The innermost ring in the figure shown is the kernel, and that's a highly privileged one. So any activity done through the kernel has to be initiated by something like system calls that have highest priority, highest privilege. So only the most privileged applications, most privileged interfaces, most privileged systems calls only can interact with the kernel, and this way we can provide a proper protection to the system. So the mechanisms for protection is one is access control. So make sure that the proper users only have access to the resources, and this can be done through providing the user or group permissions. So any resource, for example, a file can be uh, used by three types of users. One, you can say the owner of the file, the one who created the file, and the second one is the group members to which the owner belongs to, and the third one is the outsiders or the others. Every file can have three types of access control. It can be read only, or it can be read along with write, or even we can execute the file or the executable file if it is, so we can even execute it. So a user can have three types of access, maybe read, write, and execute. So that is what under the Unix version we can call it RWX, R for read, W for write, X for execution. Three types of users. So the first set is about the owner, second set is about the group members, and third is others. So if we want to say that the owner has got all the rights, so can read, can write, as well as can execute. So for the first group, we can say RWX. For the group members, maybe only read permission as well as execute permission may be given. So they can read the file and they can use the file for execution. Then it will be R dash X. So they cannot modify it, they cannot write on that, so they cannot overwrite the file. So they have only permission to read and permission to work with it, but they cannot modify. So in that case, read is there, so the execution is there, write is not there. So the positions are fixed. First position for read, second for the write, third for the execution. And group members have only right to read, right to execute, but not right to write. Then we can say R dash X. And the outsiders, they may be only allowed to read, in that case R dash dash. So that's one way. It may be owner only wants to use it, none of others are allowed to use, then it will be the first three things says as RWX, and second three says dash dash dash, and third three says dash dash dash. That means first one is for the owner, second one is for the group, dash dash dash. None of the group members can read or write or even execute, none of them. And outsiders dash dash dash, neither allowed to read nor to write nor to execute. So that way, each file can have different combination of read, write, execute for the owner, for the group members, and for the others. So depending on the situation, we can allow some to use, some not to use, and all that. So that way, we can protect the files and the resources and all that. Then we have domain security. That means there are some services which do require high privileged users or high privileged system calls. So through them only we can access. Uh, so we have some applications or the services that are directly interacting with the hardware. So definitely has to be worked with uttermost care, and all these things are put under the kernel, and kernel activity is allowed only by the most privileged users or the application interfaces or the system calls and all that. So when we are working with a kernel, then we need to work to the operating system in the kernel mode, and when the user application is being run, then it will be run in the user mode. So when it is running in the user mode, then in this situation only the green colored applications are accessible to the user, and only the green one will be working under the user mode, and any other say ring 0, ring 1 or ring 2, then they require appropriate permissions, so they may be working under kernel mode and all that. So different modes of things, so user mode, kernel mode and all that are created only to ensure that proper protection is given to our services, proper protection is given to the resources, proper protection is given to the files and all that. Now coming to the security issue, so there are many threats we have as far as our data is concerned. So we need to make sure that the data is secure. So there are various threats we have like malware, DOS, or unauthorized access and all that. So looking at the various types of malware, the figure shows that there can be a ransomware. That means they uh, catch hold of our resources and lock them, and then ask for some ransom to release the resources. So they can have control of our resources, like some files in our system can be locked by them or blocked by them, and they ask for some ransom. Only when we give money to them, they will open it. So that's usually blackmailing type of actions. Then we have something called spyware. So these types of threats just enter into our system and keeps looking at our data, what our transactions going on, what all data we have, and silently will be sending to their owner, and all the data will be stolen from our system and being sent to the owner of the spyware. Then we have something called adware, which creates problems through the ads. Then we have worms, so they just come from one application into our system, maybe a mail or something, and then spreads across our whole system. So every file in our system gets corrupt because of this. So it's just like a worm. One worm enters our system and then it multiplies and grows, and the whole system gets disturbed. Then we have trojans, which make malware into our system, and then they just start creating, corrupting our system and all that. And then we have botnets that turn our PC into a zombie, just makes our system just sleep forever. And because it's not going to be awakened directly, then the whole system becomes unusable and all that. So these are the various types of malware, and we should be able to somehow ensure that none of these enter into our system or they become active into our system. Or if they are entering into our system, we should have some watchman system that can make sure that whatever comes in is safe, and anything found doubtful should be stopped, and the user should be made aware that such a thing is happening, and let the user take care of what to do with it and all. Then looking at the defenses, so authentication is one of the important things. So whenever we are trying to use the important components of our system, then only authorized user should be allowed to enter into it. So that can be done through authentication, like username, password, or even biometrics today are used. to ensure that only the proper user is allowed to interact with our system. The other thing is to make sure that never use the data in the form as it is. So try to modify the format of the data so that anyone getting the data may not be able to easily understand it. So that's where the encryption comes into picture. So this is very much useful when we are talking about the data which is there in the backend or the data which is on the communication line. So whatever it is, so we must ensure that the data, whatever we have, should be put in the encrypted form so that whenever we want to use the data, we should be having a proper method to decrypt it. So that method is known only to the authentic users and others will not be knowing how to decrypt it. Therefore, we can secure our data and the system through encryption. Also, we can have firewalls. So whatever is entering into our system should cross through the firewall, and if it satisfies the conditions of the firewall, it is allowed to enter. If there is any problem found in the data coming in or the file coming in, then it is stopped to enter into our system. So this firewall is very useful. So firewall is one of the applications of the operating system, so that makes sure that the whole thing is put under a firewall, and anything outsider will not be allowed in without a proper check. Only authorized systems, authorized applications, authorized users will have access to the resources and all that. And then anybody is trying to intrude will be detected and make sure that the intrusion is not allowed, and proper warning system is used and all that. So that's all about how to protect our system and how to make sure that our data is secure and all that. So all these functions are taken care by our operating system. So our operating system, along with the process management, along with the memory management, along with the file management, along with the disk management, it also makes sure that the whole communication or the data residing in our system, all the files, everything is well protected from the intruders, from the malwares, from all other threats. So the protection is given and the whole system is made secure. So that's all introduction about the protection and security. More issues uh, about introducing some more activities done by the operating system will be taken care in the next sessions. So please keep watching. Don't forget to like and subscribe our channel. And if you find this interesting, please tell your friends to go through and follow. Have any queries, please do write in the comments. So keep watching. Thank you.
To operating systems is regarding the distributed systems. So distributed system is a network of independent computers. Here, independent computers are interconnected, and the mainly two types of distributed systems. One, what we call a centralized distributed system, where there is one server, and to this server, multiple clients are connected, and all the clients interact with the common server. So the server will have all the computing facilities and the storage facilities. Clients will have a smaller facility, just sufficient to interrogate with the server. So the client will send a query to the server, and server in turn gets this query and then looks for the solution and sends back the solution. So that's
how a distributed system started working. So one system can be made useful to multiple clients, and then we have another type of distributed system where each client is independent entity in itself, not like a client server. The major role is played by the server. Here, each client is client as well as the server, and they are interconnected to one another. So we call it a peer-to-peer connectivity. So here, the interconnection may help in sharing the data, may help in sharing the results and all that. So we have the positive part, then along with that there has to be some negative side. So challenges are there like consistency, then communication latency and all that. So just looking at some of the challenges a distributed system faces is one is the heterogeneity. That means each client in the distributed system need not be homogeneous with other systems. It can be uh, differently made. So heterogeneity is one common problem. So whenever two systems are trying to communicate, then it has to have a common protocol. And if they are working in different platforms or different protocols, then it becomes difficult. So we need to have a translator in between so that a common protocol can be defined and all that. Then comes the security issue because now we are allowing others to enter into our domain. We are allowing others to enter into our region, and by allowing others to enter into our region, we are uh, opening up with a threat. So there will be definitely threats. So there will be security issues. We need to be very much serious about how to maintain the security and all that. In spite, we are allowing others to interact with our system because we are dealing with distributed systems. So instead of having one system do all the work, we can distribute the works to various systems and make sure that all the systems can do the works parallelly and come out with a solution at a faster rate. So for that we thought of having distributed system, but this interaction is definitely going to create a security issue. So we need to be very serious in this. Then fault tolerance. Here there can be faulty systems on the way, so there has to be a problem. Next thing will be the concurrency problem. When we have resources that are being shared among the multiple systems, then their concurrent request can occur, and because of this we do have problems. Usually when the resources are being shared, mutual exclusion is what we need to maintain. So make sure that any given time only one client can make use of the resources and others should keep waiting till the resource is free. But it may happen that two systems look at the resource at the same time and both of them find that they are trying to see the resource which are free, and both feel that they are free and they start using them. And because this action happens in concurrence, so both of them start using the resource and that creates a problem. So we need to ensure that in spite of concurrent activities, the whole system should work in order. Then a question of scalability, how many of the systems can be connected under this distributed system. So what would happen if the number of systems increase, how things change in the about openness, about mitigation, migration, and load balancing and all. So then uh, we are working with multiple systems. Each system is provided with some sort of actions, and if one system wants to move out of the distributed world, then who should take care of that particular load? So there has to be some load balancing protocols and all that. So there are many challenges when it comes to distributed system, but along with that, there are many advantages also. Then looking at some special purpose systems for which we need to create operating system on tailor-made basis. So one is a real-time operating system. Yeah, real-time. That means the response time should be as small as possible. So if we are trying to work with a system and if that system operating system is very slow, its response time is very slow, then we miss the bus. So to make sure that the response is fast enough so that the real-time activities can be taken up, then we should ensure that the size of the operating system is as small as possible. A tiny micro or a tiny operating system is what is required to ensure fast response, no delays and all that. So there are basically two types of real-time operating systems. One is a hard real-time operating system and the other one is a soft one. So the hard one is one which where the deadlines are critical, so there is no chance of delays and all that. When it is said that after 10 units of time the result should be ready, that means it should be ready for exactly 10 units of time. Cannot go on to the 11th unit of time also. There is no flexibility, so the deadlines are highly critical, and if anything goes beyond the deadline, then catastrophe can occur. So this hard RTOS enforces strict timing constraints where missing a deadline can lead to catastrophic failures. On the other hand, the soft RTOs are flexible. So the example for hard RTOs can be robotics, whereas for the soft RTOS is streaming. So when you are streaming the live videos and all that, sometimes it may get delayed, but what we actually do there is instead of streaming regular videos, we stream in terms of packets. So one packet at a time, we just keep on passing on. So the video works at a slower pace compared to the data being transmitted. So for 1 second of video, it requires say 30 frames, then 30 frames, some number of pixels and all that. That is for 1 second, and this 1 second duration of the data, if it can be transmitted in say milliseconds, then everything works smoothly. But now and then something may happen, it may be delayed, so we find that the videos sometimes get stuck, but doesn't make much difference. So that's real-time systems. Sometimes it may get stuck, but it doesn't make much difference. Yeah, we need to wait till the video continues. Okay, not a big issue, but in case of robotics, like examples, this type of delay cannot be tolerated. That is a hard RTOS, soft RTOS. So there is something in between which we call firm RTOS, where it's a balance between the two ends. So deadlines we can miss, but missing deadline cannot create much problems. So that's some details about the special purpose system. Then we have embedded OS. So that means the operating system is embedded onto the processor itself. That means the whole operating system should be dumped onto an electronic memory, that is a RAM or EEPROM or EEPROM. Whatever it is, the size of the memory will be small, so that the whole operating system should be designed such that it consumes very small space. So mostly only kernels are used for such a operating system. So it commonly used in case of IoTs and the systems which are controlling the various components of the cars or automobiles. Any such things, they do require embedded operating system, because the whole operating system should be embedded onto the processor itself for fast response and efficient response. Then we have multimedia operating system, which is mainly worried about the bandwidth and the quality of service management. Now looking at various environments that a computing system can have, it may be a personal computing environment, time sharing computing, or client server computing, distributed computing, grid computing, cloud computing, cluster computing, various types of computing environments we do have. So starting with our traditional desktop or server, then we have mobile operating systems where it can be iOS or Android. Now it makes use of input output, better sensors and better actuators, touch screen and sensors and all that are implemented into this. Then we have cloud. Cloud is a best example for virtualization. If we are implementing a project, say an on-site project, then it consists of so many various components like applications, data, runtime, middleware, operating system, virtualization, servers, storage, networking. So if we implement it on site, then everything we need to manage. But if we make use of cloud, then there are many ways we can get the service from the cloud. One is infrastructure as a service, wherein virtualization, server, storage, networking, these are taken care by the service provider, whereas the upper layers we need to manage ourselves. If it is the PaaS, then we only have to worry about application and data components. Rest of the things is taken care by the service provider. And if it is software as a service, then all the components are taken care by the service provider. Then the environment can be looked into this triangle where we have what we call cloud, which is consisting of data centers. So there are thousands of data centers, and then we have under the cloud we have fog, so which are made up of nodes. So there are millions of nodes under thousands of data centers, and each node consists of devices, so which we can call an edge. So cloud consists of fogs, fogs consist of edges, edges will be having devices. So there are thousands of clouds, there are millions of fogs, then there are billions of devices in the overall system. So that's how this whole system is arranged. So that's something to do with introduction to the operating systems. The
Another
first part,
session on operating systems.
we have
Now
many issues
let's
to discuss.
get into the second part of the module 1, where we look into the various services available with operating systems. So let's jump into the operating system services. Just before getting in detail about the services, let's just quickly look at what operating system is. So operating system is an interface between the user and the player. So makes the user's actions simple. The operating system is the one which gives a abstraction of the hardware to the user, makes the life of the user simple, and makes all the devices connected to the hardware work appropriately and more efficiently. So here we have hardware. On top of the hardware we have an operating system, and then on top of that we have application programs, and user is allowed to interact only with the application programs. User is working in the user mode, and other important activities only will be working in the kernel mode. The user can interact with the application programs, like a user can open a Word file or open a Word document or any such thing. So that's an application. And when user tries to open a Word document or the Word program, then the Word program will interact with the operating system, and the operating system in turn will provide a space for the program to be stored onto the main memory and becomes a process, and appropriate memory is allocated for the code, for the data, for the stack and all other things. So all these services are provided by the operating system, and operating system is hiding the real hardware from the users and the application program, and makes things simple. So we don't have to bother about what hardware we are working with. Is it a Intel processor or is it a Mac processor or anything? Can be anything. Doesn't make any sense. Operating system takes care of what is behind in the hardware. Doesn't allow or doesn't make the user to bother about all that. Even the application programs also don't have to worry about what hardware on which they are trying to execute the application programs. So this operating system is taking care of all that. So that's a operating system. It's an interface between the user applications and the hardware, and makes the things more efficient, smooth working and all that. So that's a role of operating system in a computer systems. So the various examples of the operating system, it may be Microsoft's Windows. Started with a disk operating system. Now we have Windows. Apple's operating system. We have Mac operating system. We have Linux operating system. We have a version of the Linux operating system, Ubuntu. Then on the server side we have Windows servers and all. So many versions are available. Many companies are coming out with many versions of the operating system. So these are some examples of the operating systems. And operating system is mainly meant to provide a user interface with the system. We had began our journey with a command line interface, where every information is given to the machine through the keyboard. So it was only the command line interface. Through keyboard it was possible, and every activity we had to work only through keyboard, and it appears to be too hectic for a common man. So to make the things simpler for the common man, the graphic user interface was introduced in the Windows and later versions. Under DOS, it was only the command line interface, but Windows onwards, we had a graphic user interface and make the things easier. Just a click away. Instead of typing everything, we can just click the mouse and scroll and all that. So the things have become simpler because of improvement in the operating systems. Now let's look at how the users interact with the system through the operating system. So users are directly allowed to work with system softwares, application software. So we have two types of softwares. One is the system software which control the configuration of the system and all that. Application softwares are the applications provided to the user. So user usually is connected with the application softwares, and these application softwares will make the life of the user simple, will give most of the template available, only fill in few uh, missing gaps, so that way things become simpler because of the application softwares. And these application softwares will interact with the operating system. Operating system doesn't allow the system software or application software to look into what actual hardware is and all that. So the whole interaction between the user and the actual hardware is done only through the operating system. So one reason for that is giving abstraction to the user or to the application, so that what actually the hardware is, the application don't have to bother about, the user don't have to bother about. It's a operating system which takes care of all this. And next thing is providing a proper protection and security to the system, so the users uh, will not be allowed to directly interact with the hardware, so that they can create some sort of problems. So whatever the user wants to do has to do only through the operating system, and operating system will allow only the valid operations from any user, so thereby protection to the system and security to the data and the files is provided. The various services provided by the operating system to the users. So the important service provided is in executing any program. So the program, what we call a code, is called a program as long as it is in the backend, that is the secondary drive. But when you try to execute that program, when you want to run the program, it comes on to the main memory. On the main memory, that is the RAM, and once it comes onto the RAM, there is code for that, and there is memory reserved for the data, there is memory reserved for the associated stack and all that. So all the memory together will become what we call a process. So it's a live one which we call a process, and this process is executed by the operating system. So main purpose of having operating system is to execute any program. So in this we have the program on the RAM, and the CPU interacts with the RAM, and one time one operation is performed. So it fetches one opcode or the code for one operation. So each operation is given a code which we call opcode, and the opcode is fetched, and if that opcode or that operation needs some data with it which we call operands, then it will fetch the operands from the program and then makes the execution possible. It executes the instruction and the results are stored appropriately. So one instruction at a time it just takes on and runs the process. Next important activity done by the operating system is about the IO operations. So as we discussed earlier, that whole system is interconnected through what we call bus arrangement, because we know that there is one processor and one processor can anytime interrogate or can send or receive data from one of the IO devices, not more than one. Therefore, there is no point in connecting each IO device separately to the processor. So what we can do is we can connect all of them in parallel to the bus, and whichever device is to be used, only that particular device is kept live and all others are put on sleep mode. So only one of the devices will be active and all others will be made forced to be inactive, and communication between the CPU and the IO device takes place through the buses. So all these operations are performed through the operating system. So operating system will take care of all these operations and ensures the addressing of each of these IO systems and all that is taken care by the operating system. So that's what we call IO management of the operating system. Then it's what is about the file system. So there we do have at a highest abstraction level what we call application program, and then it becomes a logical file system. Then it goes into the file organization module, then the basic file system, then we have IO control, and finally device. So somewhere in the secondary drive this file has to be stored. So where it has to be stored, so that is exact at the device level we talk. Then are we storing or receiving, then what format we are trying to do, and that all IO control we have, which sector, which track and all that if it is a hard drive. Then we have a basic file system, what the file is, what file consists of, and how the file is defined, structure of the file and all that, and then file organization, that means directories and all that. So this whole system is taken care by the file system or file management system of the operating systems. Then takes care of communication and error detection and all that. So there is the sender, there is a receiver. The sender sends the data, receiver receives the data to make sure that nothing wrong happens on the way between the sending end and the receiving end. We do have something called error detection. So we have error detection, error correction facilities that's provided in the operating system. So the two systems can communicate with each other. So for communicating, we do have some standards defined, what we call as protocols, and then protocols will define the standards, how the data should be transferred, where the data should be transferred, and all more details will be defined in the protocol. And when the communication is taking place and when the file is received from the transmission line, then we need to verify whether the received file is intact or done something wrong. So for that some error detection techniques are there. So one option is just detect the error. If it is whatever you received is error free, then use the file. If it is having error, then you can request to send it again. If resending is possible, then there is no problem. But if resending is not possible, then the whatever we have received, we should make sure to use it. So we need some more stronger version of error control, which we call error correction. Yeah, correcting an error needs a lot of logic, but detecting an error is simpler compared to correcting an error. So, if retransmission is possible, then better go for retransmission and just check whether the file received has error or not. If it has error, ask for retransmission. No error, use it. But in some cases, like we are getting the data from the satellite and all that, which we cannot get again and again, like weather data or any such thing, then only once it is possible to receive the data, then we should somehow use it. So we should be ready to spend a lot of resources on that to correct if we receive the data with error and all that. So that's all the operating system will take care of. So there are some services for system efficiency like resource allocation, then accounting, then the protection and security. All these details
The
we are going
introduction
to
to the
look in
system calls.
coming session.
System call is the one that requests programs to make the operating system kernel to perform privileged operations or access resources that are not directly available to the user program. The main purpose of the system call is to keep the important resources away from the users so that misuse or malfunctioning can be avoided, and the system calls will be acting like a bridge between the users or the user applications and the resources. The resources will be working in the kernel mode and the users are working in the user mode, and whenever the user wants to get the access of the resource that is precious, then it has to work in the kernel mode, and that's the work done by the system call. System calls are the interface between the process and the operating system. So let's just check how system call works. So this diagram is showing the user process is executing and it is executing in the user mode, and whenever it wants to use some important resources, then it has to go into the kernel mode, and user don't have right to work in the kernel mode. Therefore, the user has to make use of what we call a system call, and the system call will get thing into the kernel mode, and through system call only we can go into the kernel mode, and only in the kernel mode these resources are accessible. So to ensure safety and protection, system calls are very much useful. So the user program, user process, user application is working in the user mode and has no access to the resources, and the access, if it wants, then it has to go only through the system call, no other way out. So it makes use of the system call, and the system call goes and gets the permission to work in the kernel mode, and in the kernel mode only the resources are available. So uses the resources and comes out back to the user mode with the answer. The user might have asked a question, the question's answer may be available with the resources, so the resources are not accessible to the user. Therefore, user will ask the question through the system call. The system call carries the question down to the resources. The resources are working in the kernel mode. Only in the kernel mode resources are accessible, so it uses the resources, executes the call, and then gets the answer and returns back to the user mode with the answer. So that's how the system calls are useful for accessing important maybe files, resources, memory, whatever it is, which is of importance, and we don't want a user to corrupt it knowingly, unknowingly, because of ignorance or whatever be the reason, we don't want it to be corrupted, so we keep it aside, keep it safe from the user processes, and only through system call it will be accessed. And by ignorance, by negligence, by mistake, user cannot call a system call. So when a user is calling a system call, then the user knows what the user is doing. Therefore, by mistake, it cannot happen. Therefore, through the system calls, we assure the protection and the security of the resources. So that's another way. So from the user's case, an application request for some information. So the application will request for a system call, and the system call will interrupt the process and switches from the user mode to the kernel mode. And once it gets into kernel mode, then the kernel mode identifies the system call, and if that system call is valid, then it is continued, and kernel function based on the system call is executed, and then the system call returns the value that are the output of the function of the kernel that is just executed, and then the return values are prepared, and these return values are sent back, and while sending back, again the execution context is switched from kernel mode back to the user mode, and then app continues to execute its earlier work, but now it has got the information what it was looking for. So it wanted some information, and that information is lying in the some resources, and those resources can be accessed only in the kernel node because they are in the kernel space. So from the user space, we have to go down to the kernel space, and that is possible only by switching the context from user mode operation to kernel mode operation, and that is done only by what we call a system call. This system call, once it switches the context from user mode to the kernel mode, then the system call is first identified and try to check what system call is wanting, and that particular operations are performed at the kernel level and the kernel mode. Because it is working in the kernel mode, the resources are available and it can extract the information, and this information is properly formulated and then sent back to the application. And while sending back, again the mode of operation is switched from kernel mode back to the user mode, and the user gets its answer and it continues its work. So this is the whole story behind the system call. So through this system calls, we keep the user applications away from the sensitive devices, sensitive resources, sensitive files, and all that. So by mistake, user should not disturb our data, document, and all that. So that's what system calls are meant for. Same thing in the APIs. So the user will request to the API. API will send the request to the server, and server will evaluate it and send back the answer, and that answer is sent back to the user. So it is the similar an example for that could be the API is one which is playing the role of a waiter here. So waiter interacts with the customers and gets the order, and then this order is forwarded to the kitchen, and the chef prepares the order, and the waiter gets the order back to the table and delivers to the table. So the interaction between the user and the chef is always done via the waiter. The customer cannot directly interact with the chef. So we have in between what we call waiter, and on similar grounds what we have is API. There are many system calls, many types of system calls depending on what type of functionality of the operating system we are using. So we can just look in this figure, there are totally five components of the operating systems: so file system, process control, memory management, inter-process communication, device management, and so on. Under each of them, we have multiple system calls. Say you want to work with the files, then without opening the file, it is not possible to use the file, whether it is to read or write or execute, whatever it is, we need to open the file. The file is there in the backend, and the file is a resource, and the user cannot directly interact with the file, because for interacting with the file, some protection is provided. The user needs some privileges. Only when the user has got a proper privilege, the file is allowed to access. So first process to do is to make sure to open the file. So while opening the file, the operating system or the file system component of the operating system will first verify whether the file is accessible to the user or not. If it is accessible, then it is allowed to open it. If it is not accessible, then error is raised. So once the file is opened, we can work with that, and at the end we should close it. We can read the file, we can write onto the file, we can see some position in the file and all that. So these are some file system calls. Then getting into the process control, so we can create a process. So we can create a process. So we can create a duplicate of the process or a child process from a process which we use a system called fork. Fork is a wonderful system call we have in the creating a process from one process. A process creates its own copy as another process. So the process which is creating a copy of each process is called the parent process, and the one just created is called the child process. So the process creates itself another copy. So this is done through the fork system call. We want to execute any process, then exec is the system call we have. And when we want to wait for some event to occur, then our process has to wait. So for that we have wait system call. And once the process work is done, we need to exit. And if we don't want any other process to exist, then we can kill the other process and all that. So that's the different process control system calls. On the same ground, we have system calls for memory management, inter-process communication, device management, and all that. So on this in detail, we are going to see in various modules in the coming sessions. So the next module will be looking at the process control, and then we look at memory management, and then we look at file management, and then disk management and all. So all these details we are going to see in various modules of the coming sessions. So that's an overview about a system call and the various types of system calls we can see in one place. Many details to come up. So please don't forget to like those videos, and please do subscribe to the channel, and have any queries, please do write in the comment box, and please share with your friends. Thank you. Under this, let's begin our journey into the system calls used for process control. So there are various system calls. Mainly the system calls useful are fork, execute, exit, wait, kill, etc. So let's see some examples. Fork is system call that creates a copy of a process. The original process is called the parent, and a copy of the process is called the child. So we have one process which creates its own copy, and that is done by calling a function fork in the process itself. The process itself will create its own copy through the call fork. So when the parent process calls a system call fork, a duplicate copy of that will be created and will become another process, which is the child process. And this child process can execute some instructions, and once the child process execution is done, it exits. Until the child exits, the parent will be waiting. So the overall situation here is, we can take an example. Say we are working on some process like Google. So when we type Google onto that, one Google page or the home page of the Google will be open. So we create another page and there again type Google, then one more Google will be opened. What does that mean is the code that creates a Google page is a one that when we run that code, it creates a page, and that page continues to wait till some other action happens, or it may be that the another process may want to use Google again, then it will be made available for that. So that's one action. Other way is when a process is doing, and if it wants multiple activities to be done simultaneously, then the main process will create multiple copies of it through the fork statement, and each child created through this fork will do some part of the work, and then when that is done, then it gets exits, and till the child exits, the parent will be waiting. So just we take an example here. So you can see that there are two codes exactly the same. So the first line is the main, then PID equal to 4, then if PID equal to 0, then child process, else parent process, what child process is, what parent process is. Look on the right side, then PID is 4, PID is 0, then child process, else parent process, then child and parent process are defined. So actually what happened is we started with a parent process, and this process will call first the fork statement. When it calls fork statement, then a child process is created. The exact duplicate of that will be created here. The only difference is in the parent process, the value of PID is the process ID of the child process, but the value of PID in the child process will remain 0. That means now parent can identify who the child is, but child cannot identify who created it. So the child's PID will remain 0, and parents gets a PID which is the PID of the child itself. PID means process ID. Every process will have its unique ID, and in this case, the child, when child was created by calling this function for, then it returns a PID. So if this is the parent process, then it returns PID of the child, and if it is the child process, the a0 is returned. That means from now onwards in the parent process, the PID variable will have a value of 3, 4, 5, 6, whereas in the child process, the PID variable will have a value of 0. Now the next thing is very important. So if PID is equal to 0, That means it checks itself what is PID variable I am carrying. If it is 0, that means we are referring to the child process, because child will get back a 0 to this PID variable, whereas the parent will get the ID of the child. Therefore, the PID equal to 0 condition checking fails in the parent. Therefore, the else statement gets activated and the parent process continues to work. But on the child side, PID will be 0 because it is a child process, its process ID will be 0. Therefore, it gets into the child process and the child process continues to execute. So we can define two different processes, what parent should do and what child should do, and the parent will do defined under parent process, what child should do defined under child process, and the same copy are there, two copies are there on the memory, two processes, two codes, exact two codes, but we have data, separate data for this, separate data for this. Under this data we have a variable PID whose value is 3456 in this case, where it is referring to the parent, whereas in the data field the PID variable will have value equal to 0, which is referring to the child process. So through this what we do is we can have multiple process running. So most common application of fork statement is when we are working with a child client server process, where there is a server and initially the server will be waiting for some client to query. So when a client sends a query to the server, and if server starts answering the query, then other clients cannot be acknowledged. So to make sure that multiple clients can be acknowledged simultaneously, what actually happens is when the server program or the server process will be waiting for a query from the clients. When the query from the client comes to the server, simply server creates another copy of the server and says that you take care of this client and let me continue waiting for another client. So one client comes for a service, then the server creates copy of itself and attaches that client to this server and says that you take care of this client, and the original server continues to keep waiting for new clients coming with the query. When another client comes with the query, another copy of server is created and that another copy is attached to the second client and waits for the next one. Another third client comes, third copy is created, attached to the third client, and this continues forever. So the original server code is meant to wait for the new clients to come up, and whenever a new client comes up, just a new copy of that is created, its own copy is created and attached to the client. So that's the concept of fork, which creates its own copy and makes the code or the new copy of that which we call child to continue serving the process. So that's about the fork. That's execute, exit, wait. In this example, the example of what we are talking about here in the flowchart is a parent is not going to do anything, it just keeps waiting, and when a fork, whenever we want the process to do some action, a child is created for that, and that child will continue executing whatever is requested, and once the execution is done, it exits. Till the child exits, the parent keeps waiting. That means if a parent process is activated, then it should remain active till all the child processes created by it are active. So it should keep waiting till each and every child gets exited. Only when all child processes get exited, the parent process can exit. So it keeps waiting. So that's about the process control system calls. More details to continue. So keep watching. Thank you. We are into the system calls used for process management, and under these system calls, one of the important system call is a fork. Fork is one of the important essential component of any process management. So let's just look at what the fork system call is to do. So most of the cases we would like a parent to create its own copy so that the parent can continue working one way and the child continues to work in another way. But in reality, the two codes are just a copy of it. The code will be a copy of that. It's not a separate code. It is the same code duplicated onto the memory, and that is done through the system called fork. So when a fork is initiated, the parent process, which consists of many components in the memory. So the parent process occupies the memory for various components like code, static variables, heap, IO descriptors, registers, stack, and all that. So that's a parent process, and when we inside the parent process, there will be one instruction that is called fork. So when that fork instruction is executed, the system called fork is executed, then we have two copies. One copy, the parent itself, and the exact replica is created in the memory, where the heap is copied, static variables are copied, the code is copied, but the stack and registers, IO descriptors may have different values, and the process table now will have two processes. One, the parent process, now here it is called X, and the child process, which is referred here as Y. So there is, if you look into the memory way, then there is memory where the parent process is occupied, and when we run one fork, then a copy of that is created, which is a child. Say once we have created, one child is created, and then one more child is created, then one more child is created, and so on. So in reality, what is happening is the original code is being copied at multiple places, and each one will be working differently. That depends on the process ID. So when a child process is created, then the child process has to know that it is the child. So for that, it will not have any process ID, so it will be 0. But the one which has created it will get a process ID of child 1. So that's what we had seen in the previous example. So again we will look into in detail. So what is the need of such a fork instruction or fork system call is, say, when you are talking about a client server system, there is one server and there are multiple clients, and anytime any client may require the service of the server. And when one client requests some service from the server, and if the server starts serving it, then it won't be able to recognize the request from other clients. So because it is busy serving the first client, so from then onwards, if any other client requests the service of the server, then it won't be able to serve others. So we want each of the client to be honored equally. In that case, what we do is when a parent process usually is meant to wait for the clients to come up. Parent process is just waiting for any client's request, and the moment it finds the request of the client, it creates a copy of itself, uh, another child process, and that child process is attached to the client. So all the services that are provided by the server are defined under child process. Therefore, now once the client is attached to a child, then the child will be able to serve the client, and the parent is now free to wait for the next service request from another client. So when another client comes up with another service request, then it creates one more copy of itself called child of itself, and then attaches that child to the new client, and this keeps on continuing. In this example, we have seen that there are three clients at present are working with the client server system. So there is one main process which we call parent process P, and that is the purpose of that is just keep waiting for service request from the client. Anytime it gets a service request from the client, a child process is created which is exact duplication of that. And then the only difference in that code is there are two components of the code in that. One component is what parent should do, and another component is what child should do. So in this case, the parent component is just keep waiting, and whenever a request comes, create a child. So fork, wait for the client's request, and once gets a request, fork assign the child to the client, and then keep waiting. So that's what a parent has to do, and what child has to do is various services that can be provided to the clients. All the services are defined under the child process, and all these two are distinguished with the ID which we call PID. If it is 0, then it is about the child. If it is not 0, then it is the parent. So the parent continues to execute the first component, that is waiting for the clients, and the child continues to work with the second component, that is to serve the client. So in this case, three clients are working, which are the carbon copy of the client as far as the code, static variables, heap are concerned. But each client may be working with different IOs, and they may be working with different functionality may vary. Therefore, the stack and all that are separate. So copy of the heap from the parent is copied onto the child. Copy of the static is copied onto the child's memory part, and the code is also copied, and the registers and stack details are maintained separately. Parent is having its own work, child is having its own work. So looking at what exactly happens, so this was the parent process, and first it is calling a fork, so it is creating a child process. So whenever a fork is executed, then a child process is created. Now you can see that the whole code is exactly same. Only difference is in this case the PID is 3456 and in this case PID is 0. So every child will get a PID equal to 0 and a parent will get a PID which is not 0, that is the actual process identifier of the child. So the parent should know the ID of the child and the child need not know the ID of the parent process. Therefore, if look at the code, if it is PID is 0, that means it is to do with the child process. So child process defined here, it will work. So here we have defined all the services that are provided by the server to the clients. All the services are provided, and the parent process is just a indefinite loop which is just waiting for uh, client's request. So whenever gets a client request, fork statement is executed and then a child is created, and that child now continues to uh, work for that client, give all the services the client is requesting. At the same time, the parent continues to wait for the next client to come up. When a next client comes up, another fork is executed, one more child is created, and that ID is also provided to the parent. In this case, we are only talking about one child is created. We can have multiple childs created. There, instead of having one PID, we will be having a list of PIDs. So one for each of the child, and then the logic will be little different. The parent process has to exist as long as all the child press as long as a child process is working. When all the child processes are exited, only then parent process can exit. So parent process cannot exit as long as at least one child is working. So just to make sure that all child have exited, it keeps looking at which child it has created and what is its status and all that. For that it needs PID of the child, whereas the child doesn't require PID of the parent because the other communication is not required. Parent's activity child is not going to monitor, but child's activity parent is going to monitor. Therefore, where the child is, what is its ID and all that should be known to the parent. So this simple arrangement will help us in defining two processes in one code, and this whole code is just copied as it is. And if PID is 0, child process runs. If it is not 0, parent process will run. So in this case PID is 0, therefore child process will run. In this case PID is not 0, therefore parent process will run. The parent process in case of client server system, the parent is just to wait for the new client to come up, and when a new client comes up, another child is created and attached to the client. So this is what a fork is meant for, and the most essential component of process control is the fork system call. So that's some additional details I wanted to share regarding the fork. Hope give more clarity on this types of system calls. We continue, we have seen about process control system calls. Now we look at other system calls. So let's begin with the file management system calls. for managing the files. The system calls like creating a file, opening a file, reading a file, writing a file, closing a file are the various system calls which we require whenever a user wants to create a file has to use a system call because the user is working in the user mode and any file operations will be done in the kernel mode, so the switch of the mode has to take place from the user mode to kernel mode, and that is possible only through the system calls. So whenever any file operations are to be performed, so we do have system calls. The system call is there to create a file. So in the agent figure you can see that we are creating a file. We can open a file. So we are saying f open and we are giving the name of the file, and then we are saying what we need to open it. We have to just read it or write it or even execute it and all that. So in this case demo.txt is the file name and we are opening for writing. And if the demo.txt exists in the directory where we are working in, and then if the user has a authority to write on the file, only then the file will be open. And when the file is open, some more than zero value is written and that is stored as a fp. If the file does not exist, or if the file is not available in the directory, or if the write privilege is not for the user, then the file will not be opened and you get a -1. So we need to verify whether it is -1 or not and then continue working. If we get a -1, that means the file is not open. Want to read the file, so we can have read, write, and finally we need to close it. So here we are using getC, putC are the two functions. So putC, it takes from the character, puts it on the file, so this is for writing, and getC is gets from the file and prints it. So the getC is a system call that gets the one byte or one data at a time, and that is put in the loop till we reach end of the file. Same thing happens here also. So these are the various system calls we have for operating the files. Then these files do require access control, and these access control are in three types of access control we can provide. We can provide a user only read access or write access or execute access. So we can allow some user to read a file, or we can allow someone to write onto the file or modify the file, or even can allow someone to execute the file and all that. So in that we have R means having a authority to read, W means having authority to write, RW means read, write, both can be done. So in here we are shown with three positions, and we have three users here. So the first position, so these three things are talking about the three files. So this says we have a file 1 and has got two connections. That means the user 1 and user 3 has access to file 1, and both of them have read access only, and user 2 Bob does not have access to file 1. Same way, file 2 Alice will have a write authority. Bob can only read, but Fred cannot read or write or anything. Same way, file 3 Alice can read, write, Bob can only read, Fred can only read, and all that. So these are the what we call the file metadata. So the information about the file, about regarding who can access the files and all that. So these details are stored in the metadata, and whenever the user tries to open or work with a file, then this system calls will first verify the access control metadata, and then make sure that whatever operation the user is trying to perform is a valid one, is allowed one, and the user is privileged to work with the file the way it is expected, and if it is so, then it will be allowed, otherwise error is raised. So that's about the file management, and then we'll get into device management. The devices, as we have discussed earlier, that anytime only one of the device can be used because there is a single processor. So when we have such a thing, then it is better to work in the form of a bus. All the devices can be connected to the bus, and through the bus all the operations can be performed. So if we want to interact with any device, then first thing is we just request that we want to use the device, and if the device is ready, it will be available, and once the work is done, we release the device. And then we were trying to read or write from the devices. So if we are looking for the reading, then from the input device it gets to input controller, then we have input device driver, so that it talks about the protocol in which the input device is working and all that, and then it gets into the ready queue, and the data whatever is read is put on the ready queue, and whenever CPU is free to read the data, it can read. The only reason why we have queue here is the CPU's working speed and the IO device working speeds do not match. Therefore, in order to optimize the CPU's working, we just make the IO operations in the background, and once if we want to read something, then the CPU will inform the input device to read something, and then it just continues doing its own work. And when the input device reads the data, then puts onto the queue and informs the CPU that the data you have requested is ready on the queue. Whenever you are free, just go through it. Same thing happens whenever CPU wants to write onto the device, then it just dumps it on the output device queue, and then this data goes to the output device driver, and then it verifies the protocol and the way it is to be written and all that, and then output controller, and finally it goes to the output device. So these read write activities we need to look in detail in the future sessions. So that's what happens with device management. Then we have some system calls that is meant for information maintenance and communication. Like we do use timers, and for timers we just set the timer, we get the how much time has elapsed and all that. So in case of scheduling and all that, as we discussed in the earlier session, process control session, the scheduling, each process is given some slot, and to make sure that after the slot is over, the process has to stop, and the control has to go to some other process and all that. So this all these activities are taken care by the timer, and set timer, get timer, and all that are the functionalities provided by the information maintenance and communication component. And one of the important activities taken care by the system calls is inter-process communication. So there are multiple processes working in that, and if we want to communicate between the two processes, then again each process is working in a user mode, and to ensure that inter-process communication takes place, one option is have a shared memory, so that both the process A and B have authority to seep into and peek into this memory and read and write into this memory. And if process A wants to share data with process B, then process A will write onto the shared memory, and process B will read from the shared memory. So this way the message is being passed from A to B via shared memory, or otherwise the message can be passed from process directly to the kernel and from kernel back to the other process. So different kinds of process controls, inter-process communications are possible. So that's about the system calls, various types of system calls we have seen, and more details in the coming sessions. In the future modules, we are going to see all this in more detail at the implementation level. So till then, keep watching. Thank you. Hello friends, welcome back to another session on operating systems. Now let us see what system programs are. So they provide the environment for program development and execution of the programs. Definitely they are not part of the kernel, but they interact with the operating system to make the user interact with the operating system through the system programs. So just to make sure that system program is different from the operating system, because usually system program means there's a confusion that they misunderstand with the operating system. So let's just briefly look at what the operating system is, what the system program is. So the role played by the operating system is a core system software that directly manages the hardware. So the role played by operating system is it is the core system software that directly manages the hardware. On the other side, the system program, the utilities that provide a user-friendly environment. So they make the user life easier, providing a user-friendly environment. So these are the utilities. Looking at the location, the operating system is located at the kernel level, whereas the system program just sits above the operating system. The components of the operating system are the kernel, device drivers, memory manager, scheduler, etc. Whereas on the program side, if you look at it, system program, they are the file editors, compilers, shells, status tools, etc. The responsibilities, if you look at them, the operating system is responsible for process control, memory management, IO management, device management, file management, and the security. Whereas the system programs are responsible for file handling, program compilation, user commands and communication, and so on. So without example, we can't understand what exactly we are trying to say. Operating system examples like the Linux kernel, Windows, NT kernel, and so on. Whereas the system program, Bash, ELS, CP, GCC, Nano, and so on. ELS is the one we in the Linux used to open the list of the files or open the directory and shows what all files the directory contains and all that. So GCC is a compiler program. So the access to the system, the operating system has direct access to the CPU, RAM, and all other devices, whereas the system programs use the APIs or the system calls to interact with the operating system. Say though the system programs don't have any direct access to the resources like CPU, RAM, and other devices, they have to go through the APIs or the system calls, as we discussed in the previous session. As far as the installation is concerned, if you want to install the operating system, it comes bundled with the operating system, whereas the system program can be added, removed without affecting the core operating system. The user, the applications and the system programs use the operating system, whereas the system programs are used by the users and the developers. So user use the system program in turn use the operating system in turn give the access to the devices, CPU, memory, and all that. So that's how the whole system is done. So looking at the categories of the system programs, so we have system programs that can manage the files, that can provide the status of the system, file modification, programming language support like compiler and all that. program loading and execution, communication, and all. These are various types of the system. Hi friends, welcome back to another session on operating systems. Now in this session let us see the structure of operating system, various structures we have for the operating systems. The simplest structure is about the Microsoft Disk Operating System, very famously known as MS-DOS. So in that the bottom layer we have ROM, where the basic input-output system, device drivers and all are put in that, and then other device drivers are there on the upper level. Then we have resident system programs, and finally we have application program. So that simple structure is for MS-DOS. Then we have a layered structure for Unix like this, where the innermost layer, that is the bottom one, is the hardware. Then we have layer 1, layer 2, layer 3 and so on. So the layer 1 will directly interact with the hardware, that is layer 0, whereas layer 2 has to interact with layer 1, and if layer 2 wants to interact with the hardware, then it has to interact via layer 1 only. So that hiding is provided, security is provided, so that the upper layers cannot directly interact with the hardware. Only layer 1 will have privilege to interact with the hardware. So if we seriously design the layer 1, then the protection and security issues can be very well taken up. So that's the advantage of working with a layered operating system. Then we have a microkernel operating system, which is used in Mac systems. So in this case what happens is we have a hardware, and on the hardware we have a microkernel, that is only the essential components of the operating system are put in that, and we have a microkernel, and on that separately various system programs are written, like application, IPC, there's device drivers, Unix servers, file servers and all that, and these are interacted by the applications. So the applications have to interact to the various system softwares, and through system softwares only they can interact with the microkernel, and through microkernel only any interaction with the hardware is possible. So this we have a parallel possibility when we are working with a microkernel operating system. So we can have a separate path from the application via some application like device driver, then to the basic IPC, and then finally down to the hardware. So we can have multiple sessions working parallelly. But yes, there has to be something called scheduling, which ensures that any given time only one of them is active, all other things are inactive. And then we have modular, again that's a Linux version where a core kernel is created, and then all other device drivers and other things are put as various modules. So depending on the situation, so at the basic level, when we switch on the machine, the core kernel will be loaded onto the memory and it starts working, and then depending on the situation, various modules are put on the memory, and whenever the process do not require any of these modules, then they can be just removed from the main memory, so that with the limited memory a lot more activities are possible. Say when we are working with file system, only then we interact with the file system module. So we need a file system module onto the main memory only when we are working with the file system. If we are not working with file system, then this module is no more required on the memory, so that we can have limited space used at a maximum efficiency. So that's various structures we have for the operating system. Many issues to be discussed in this series. So keep watching. Thank you. Hello friends, welcome to another session on operating systems. So now let us see what a virtual machine is. It's a very well-known term, quite oftenly used virtual machine. So let's see what a virtual machine is. A virtual machine is a software-based emulation of a physical computer. It runs an entire operating system as if it is a real one standalone machine, but it runs inside another system. So on the hardware there is operating system, and inside this operating system another operating system will be working. So for the user, thinks that the operating system on which the user is working is directly interacting with the machine, but in turn the operating system on which the user is working may not be directly interacting with the machine, but in between there may be another operating system which is guiding this operating system to interact with the machine. So the whole thing is virtually one machine is available on for each user. A user may be thinking that is working on one type of operating system, but on the reality there may be another operating system installed on the hardware, and the other way the user may be thinking that is working on Intel machine, but in fact it may be a Mac machine working at the back end. We don't know what exactly it is, but the user feels that he is working with his or her own operating system or his or her own hardware. So that's how virtual look is created, as if the real system is available to each user and all that. So why do we require a virtual machine? So it helps us to work with multiple operating systems on one physical machine. That means we can have more than one operating system working simultaneously on the same hardware, and different users may be working with different operating systems simultaneously on the same user, of course through scheduling and all that, but the same hardware is available for multiple users through multiple operating systems and all. So this virtual machine provides an opportunity to have the user feel that they have their own machine, though the same machine is being used for multiple users, and each one is working on their own environment. So it will be easier for testing the software or viruses without affecting the host, because we have our own operating system working, which is limited only to the user, but the machine works with another operating system, and this interaction among the operating systems is through the system calls and all. So it's a highly dedicated one, and they are working in privileged mode, so a lot of safety can be provided because of virtual machine concept. Then it is going to save the cost, because we don't require multiple physical servers. So we can have a single physical server and can make it to work. Then we can simulate hardware and environments like IoT and other things. The benefits: we can provide isolation to the various users, we can allow resource sharing, and will be a best way of testing the software and all that without disturbing. So this figure clarifies all the doubts we still have in our mind. So we have a hardware at the bottom, then we have one operating system which is driving the hardware, and on the operating system we have an hypervisor on which we have various uh, virtual machines. Each virtual machine may be having their own operating system. So in all, what we can have is the hardware may be of one type, and that it may be working on some operating system, maybe Linux. On the Linux, one guest may be working on Windows, another may be working on Unix, another may be working on Mac, and so it is possible to have each user work with a different operating system, and that is possible only through what we call virtual machine. So gives a lot of freedom to the users, so don't have to get bound to the what actually physically available and all that. So that's advantage of working with the virtual machines. Now looking at types of the virtual machines, we have basically two types of virtual machines. One what we call a system virtual machine. The examples used were VMware and VirtualBox and all that. This emulates a complete hardware environment to run a full operating system, and provides a platform to install and run an entire operating system, which we call a guest operating system, just we have seen in the previous example. So we have hardware, on that we have a operating system, on that we can have each guest can have a separate operating system, so we can install the entire operating system on top of the operating system, which is directly attached to the hardware, and then it simulates all the physical hardware like CPU, RAM, disk, and all networks are simulated. So each user through the guest operating system feels that all the hardware is fully available, independently available to the user himself or herself, will not allow the user to think that it is being shared or it's all working in some other environment, and also we feel that we are at our own environment. So homely environment is created for each user, independent user, though each user may be comfortable with different environments. Therefore, through this system virtual machines, we can provide each user to install their own guest operating systems and work on that. And through this, each user feels that the user has access to the CPU, RAM, and all the resources. And it uses a hypervisor to manage the VM lifecycle. So we have a single hardware, therefore anytime one of the users will be active, others have to be made inactive, so it has to be somehow scheduled and all that, so that all scheduling and all activities are taken care by the hypervisor shown in the figure. Then we have another type of virtual machine, which is process virtual machine, which commonly used in Java virtual machines, where it is designed to run a single program or a process in a platform independent way. That means we don't bother about what platform we are working on. So especially when we are creating a Java process, so it doesn't really require what platform we are working on. So it just creates a code that is independent of the platform. That means the platform may be any type of operating system, or it may be any hardware. So independent of the hardware, independent of the software, it is created, and this is created when a process starts, and when the process ends it will be destroyed. So this virtual machine is attached with the process. So a virtual machine comes when a process comes to exist, and as long as the process is existing, this virtual machine will be existing. The moment the process is no more existing, this process virtual machine also gets killed. Whereas on the system virtual machine, we have created for each user one uh, whole system is virtual machine is created, so that user can create any number of processes on that virtual machine. But here a user independently creates one virtual machine for each process. And it provides an abstraction over the host operating system or CPU architecture, and also just an abstraction it provides, and doesn't emulate any full hardware, and just enough whatever is required for the process, only that part will be simulated. So that's the advantage of working with this. So when we are working with the process VM, then whatever resources are required, only the required resources are emulated and simulated, and the copy of that is available to the process. And through the scheduling, here different processes are being scheduled under each user. So in this case, the user may create multiple processes, and the scheduler takes care of the user wise scheduling, and once the user gets a chance to work with, then under that user how many processes are available, they will be scheduled. But here it's directly a process is getting scheduled. So looking at another way, system virtual machine, we have the virtual machine above which we have an operating system for each application. For each user will have their own operating system. So that's ISA, and we have ABI. We just look at what these are. But in case of process virtual machine, only application is there under ISA, whereas virtual machine operating system are part of the ABI. What is ISA? ISA is instruction set architecture. So how the software tells the hardware what to do. So it's a instruction set. So if you are working with any programming language, then the programming language has its own instruction set. Then the program is written in that using the instruction set of the programming language. So directly in that language, instruction set are used and try to inform the hardware, and it is working on its own operating system, and then gets in onto the virtual machine, that is a system virtual machine. Whereas in case of process virtual machine, only the application part is there in the instruction set. That means the user program is only available in the instruction set, whereas other things go into ABI. ABI is the application binary interface, which tells how the compiled programs interact with the system at binary level. So here at the system VM, what happens is the compiled program of any application is interacting with its own operating system defined for the user, and that operating system is interacting with the virtual machine. Whereas in the process virtual machine, the compiled version of the operating system or the compiled version of the program itself is interacting with the virtual machine, and virtual machine in turn interacts with the operating system, which further interacts with the hardware. So looking in more detailed way, the system virtual machine, we have hardware at the bottom, then we have virtualization software, and then we have its own operating system for users own operating system, and users applications. So some of the applications the user is using may require this operating system, or some of the applications directly interact with the virtualizing software and get to the hardware. That means virtualizing software is actually the operating system plus the one which is used to create a virtual environment. So the application may directly work on the operating system which is being used for the system, or the application may have their own operating system. So the user may want to work with the operating system which is different from the operating system which is working in the system. So if it is doing so, we have another one path. So application to the local operating system, then global operating system, and then to hardware. or the application wants to use the global operating system directly, then they can directly use the global operating system and interact with the hardware. So the logical level, if you look at it, the applications either go through their own operating system, local operating system, and get into the virtual world, or the applications can directly get into the virtual world if it is a system virtual machine. But in case of process virtual machine, application itself having a virtualizing software, so application interacts with the virtualizing software. So if that application requires a separate if, software, then it goes into the software installed on the hardware, and via that it goes. Or if it wants to work with some other operating system, then the virtualizing software will provide that other operating system, and then so depending on the application, if the application is written on the environment in which the whole system is running, then directly through OS it goes. Or if it is working on some other operating system, then via virtualizing software it goes directly to the hardware without getting into the global operating system. That means the virtual world is the whole thing just below the application process. Whatever is there, everything becomes virtual. Now the process itself gets into the virtual world, so each process gets a virtual world, whereas here each user gets a virtual world, and under each user can have multiple processes. So the scheduling is done in case of system virtual machine in terms of users, whereas in terms of process virtual machine, the scheduling is done in terms of process itself. So that's about the virtual machine. Then the virtual machine has created wonders in making big dreams realizable. So we can provide multi-user, multitasking, multiple operating system environment, multi-environment, all things possible only because of this virtual machine concept. So that's it for now. So please do like the videos, and if you find the videos are of any use, please do subscribe and hit the bell icon, and please tell your friends to follow the channel. Many issues to be discussed, many things to be on the queue.
Another
So
session on
please
operating
keep waiting.
systems. Today let's see what OS debugging is all about. Operating systems are some of the most complex pieces of software ever created, and are like all software, they sometimes go wrong. When they do, we need a process called debugging to identify what went wrong with the operating system. OS debugging is not like fixing a regular application. Here, you are working deep in the system, often with no graphical interface, no friendly error messages, and sometimes no room for mistakes. It's similar to trying to fix an engine while the car is running at full speed. That's what kernel level debugging feels like. So how do you think developers actually debug an operating system? First, they use logs to understand what the kernel is doing right before the crash. Next, they might turn to kernel debuggers for remote step-by-step debugging of a running system. When the system crashes entirely, developers analyze crash dumps, snapshots of the memory at the moment of failure to trace the root cause. Think of it as a black box data from an aircraft. So finally, the tools like static analyzers catch bugs in the code before it's even compiled, helping to prevent memory leaks, race conditions, and error. That's a logical errors. Debugging an operating system is equal parts art and science.
It's a detective game that requires patience, tools, and deep understanding of how things work beneath the surface. But when you finally find that one line of code that was bringing the system down, it feels like a magic. So let's see what exactly the OS debugging consists of. It's a process of identifying and fixing bugs or the errors in the operating system, including the kernel, drivers, and system calls or the startup process. So these are the various components and what we need to debug. Looking at the kernel, so the kernel may stop working, which we often call crash, may have deadlocks because of the resource problem, maybe because of the memory leak, there may be a problem, or there may be bugs in scheduling system. So all this come under the kernel, and any of this go wrong, then the kernel stops working or it crashes. At the device drivers level, there may be incorrect hardware communication or there may be crashes. At the system calls level, it may be unexpected behavior or there may be permission issues. So it may uh, provide or it may allow some user activity to work in the kernel mode, though it was not allowed to do so. That may create a problem. So this may happen due to mistakes at the system call level or at the boot process. So it may hang during the startup or it may miss some of the modules, and the whole operating system is made up of modules, and if some modules are not properly loaded, then some component of the system may not be working, and because of that the whole system fails. So that may happen during the boot process or during the process management. It may be because of the zombie processes. That means the process which was no more active but still is occupying the memory, and because of such problems, the memory is unnecessarily occupied by inactive or dead processes, and not allowing any more new processes to come up because there is no more memory available, or maybe some stuck states where the process may get stuck at some state for some reasons, and that may create a problem, or it may be due to the interrupts and IO activities. So it may be timing issues or non-responsive devices and all that. So these are some of the problems we look at during the operating system debugging at various component levels. Now, the process of debugging, when you say that it may be failure analysis, yes, is the process of identifying, understanding, and resolving the system failures in an operating system or any software running under it. So the process is discover the root cause of crashes or freezes or unexpected behavior, and then make sure that it doesn't recur, so prevent recurrence. Then because of that we have improved system stability, and the system is more reliable. So due to the failure analysis, we can understand what are the root causes of the crashes and all that, and then we can prevent this to recur, and by doing so we can improve the system stability and the reliability. Then we have another process called performance tuning. It's a process of analyzing, adjusting, and optimizing a system to ensure it runs more efficiently, quickly, and reliably. By doing this, we improve the user experience because we are optimizing the system, and because of this optimization, the system runs more efficiently and more quickly and more reliably, and because of which user experience will be a better one. and it will maximize the hardware utilization and then reduce the latency and the response time. So when we call for some activity, and if that activity can quickly respond back with the answer, with a reliable answer more efficiently, definitely the latency will reduce, response time will reduce, and handle more users and processes concurrently, because there is less latency, response time is fast, so each user can be responded at a faster rate, and because of this, in a given time, the system can address more number of users and all that. And it prevents the bottlenecks and crashes through the performance tuning. Then we have dtrace, which is a dynamic tracing, is a real-time diagnostic and troubleshooting tool which lets us to observe how the operating system and the applications are behaving under the hood. So this gives a live performance, and it makes live performance tuning without restarting the services. So while the system is running, it just tries to identify anything is going wrong, and it just looks for problems and tries to address them, and these all things happen in the live, and we don't have to stop the service and then restart it. So that's the advantage of dtrace. The system calls are regularly traced, function calls are monitored, then debugging the kernel level and user level performance issues are regularly done, and bottlenecks, memory leaks, and CPU hogs are regularly identified. And that's all about the OS debugging. The system generation is the process of customizing an operating system for a specific computer setup. We know no two machines are the same. Some may have more RAM, others may have special hardware like sensors or GPUs and so on. So the system generator lets the operating system adapt by including only the features we need. It's like tailoring a suit to fit just right, trimming away what is unnecessary and focusing on what our machine really needs. Especially in embedded systems and servers, this makes the operating system faster, lighter, and more efficient. So let's jump on to what the system generation is. It's a process of configuring and installing the operating system specific, specifically for a given hardware setup. It's done by choosing and compiling only the necessary modules and the features. And the process is the hardware survey. The hardware is first surveyed to identify the CPU type and see how many processors are there in the system, what type of RAM we do have, what is the capacity of the RAM, what all IO devices are connected to the system, and so on. And once the survey is done, then we look at the configuration choices, and we choose the features like multi-programming, file system type, scheduling policies, and all that, and they are identified for the available hardware best suited. And then it creates a system table, so builds the configuration tables like vector interrupts, device maps, and all that. So that tells, so when any device interrupts, then what action should be taken. So there will be tables like interrupt vectors, like each interrupt will have a software that has to be run. Each interrupt will enable a system call or similar, and the interrupt vectors will provide the address where that system call or that part of the code is situated, or it will tell which system call should be used for what type of vectors and all that. And the device maps, something like the device will work only when the proper drivers are set. So whenever the system is being activated, it identifies the various devices connected to that and then creates a map that which device has a what type of driver and where it is situated in the memory and all that. Once the system tables are generated, then the kernel is compiled and it assembles the selected modules into one kernel binary. So it usually is not a single entity. For each of these individual systems, there will be different modules, and depending on what is required, that has to be used. So for example, if we are talking about a keyboard, there are many types of keyboard may be possible. So for every type of keyboard, one driver will be put into the operating system, but it's not necessary to have all the drivers actively participating, because it requires only the corresponding driver for the current keyboard being used. So when it's being installed, the operating system, the hardware is surveyed, and then it just identifies what type of keyboard we have, and then looks back into the back end and see in the drivers list which driver is most suited for the current hardware we are using, and only that component is selected, only that module is selected. So that way, for all possible situations, like what type of RAM we have, what IO devices we have, for everything there will be a module, and these corresponding modules only are selected, and then all these are dumped together, and one kernel library or one kernel binary is created, and finally it's installed. So this whole compiled operating system is copied onto the boot media. So what boot media is, what booting is what is the discussion of the next session. So in all, we have a variety of various device possibilities that are to be connected. So today it's era of plug and play. So we don't have to have everything built in the system itself. We can plug and play with any of the devices like keyboard, mouse, hard drive, any maybe a PlayStation or any such thing can be just connected to the system through the ports available, and that has to be automatically recognized and made to work. So to make any device work, appropriate drivers are required, and most of the drivers are bundled up under the driver part of the operating system. But we are not interested in every driver. Whichever module is to be used, depending on what hardware we are working with, what mouse we have, what type of keyboard we have, what type of display we have connected, and all that thing. So depending on that, one particular module is required for every situation, and then all those things are selected and bundled up and created as one kernel binary, and this kernel binary is finally compiled onto the boot media. So that's the work done by the system generation part of the operating system. Yeah, of course, the confusion is the boot media, what boot media is all about. So that's what we are going to look at our next session. So please don't miss the next session. It's the most important part of
operating system, that is a bootstrap booting. That is how the operating system gets loaded onto the system. So that's it for this session. So please do like, subscribe and share with your friends, and press the bell icon to get the notifications as and when new operating episodes are released. So have you ever wondered what exactly happens when you press the power button on your computer? What follows is a fascinating process called booting, the act of waking up your machine and preparing it for the use. The moment you turn on your computer, power flows onto the motherboard and the CPU immediately looks for instructions. It is like a student waking up and asking, what do I do next? These first instructions come from the system firmware, either BIOS or UEFI, which is stored on a chip on your motherboard. Think of BIOS, that's a basic input-output system, as the machine's built-in supervisor. It starts running a power-on self-test or POST post to check your hardware like RAM, keyboard and disk, whether it is working properly or not. If anything is wrong, the system beeps or shows an error. Once the post is successful, the firmware looks for a bootable device such as your hard drive or SSD or even USB stick, and hands control over to a small program called bootloader. The bootloader plays a critical role. It's like a librarian who knows where the real book is kept. In this case, the book is the operating system's kernel. The bootloader loads the kernel, the core part of your operating system, onto the RAM. Once the kernel is in memory, it takes over and starts talking to all your hardware. It sets up the memory, loads device drivers, and mounts the file system like a stage manager preparing everything before a show starts. Finally, the kernel launches the init system, which starts all the essential background services and eventually brings up the login screen. So that's what a booting is. So let's look at what exactly the boot process is. So it's a process of starting up a computer, beginning from the power on to loading the operating system into the memory. This process continues. Basically, there are two types of boot processes. One, cold boot, which starts from the powered off state when there is no power supply. When we press the power button, a cold boot process starts, or there is a warm boot where we are restarting the already running system, like pressing Ctrl Del and using to reboot. So the basic steps involved in the booting process. So power on, electricity flows through the system. CPU gets the power but does not know what to do yet. Then starts the power on self-test. It's a firmware that checks if the hardware is working or not. The hardware like the RAM, keyboard, disk. If any of them is not working, then we can't proceed further. We need RAM to load the operating system. We need the keyboard for interaction. We need the disk from where the operating system has to be loaded. If these are not connected, then we cannot continue. Therefore, it just sends a error message, beeps, and then if everything is okay, then it continues to the next
one where the BIOS is executed. BIOS is a firmware program stored on the motherboard. It is stored in something like a permanently written memory like EEPROM or EEPROM or EEEPROM depending on the type of the system we are working on. Then it looks for the boot device where the operating system is actually located. It may be the hard drive or it may be SSD or it may be USB, and once that is identified, then it loads a small code called the bootloader. This bootloader is a small program whose job is to load the operating system's kernel. It finds out where the operating system's kernel is situated in the secondary memory, and from there it reads byte by byte and loads it onto a predefined location in the RAM. Then the bootloader loads the operating system kernel onto the memory, and once the kernel is loaded, then the kernel takes over the control of the system. So after the bootloader loads the kernel, the control is given to the kernel by appropriately changing the address of the next instruction to be executed is shifted to the first location of the kernel where it is loaded in the RAM. Once that is done, then the kernel starts the init system, that's initialize the whole system, and then it launches all the necessary services and user interfaces like GUI, shell, and all that. So that's a booting process. So booting process where bootloader loads the kernel. So when we power on, the BIOS comes onto the picture and that initializes the post, and then the kernel is looked in the disk and is loaded onto the RAM, and once the kernel is loaded onto the RAM, then the work of the bootloader is done, so the control is transferred to the kernel situated on the RAM. So these are the various activities. BIOS is a basic input-output system that executes the MBR. MBR is the master boot record that executes grub. Grub is a grand unified bootloader which executes the kernel. Kernel in turn executes the init code, and init code executes the run level programs, and finally the run level programs are executed from the various directories shown here. So that's it for now. In the module 1 we have many things in the forthcoming sessions, the other modules to follow. So thank you very much for following me. Have any doubts, please reach me on the given mail ID, and all the videos are available on my YouTube channel. So please do like, share and subscribe the channel, and hope you are enjoying the journey of understanding operating system, and wherein we are looking one concept at a time. So that's it for now. Thanks for following me. Thank you very much.